Our next chapter is the electric potential and capacitance. Okay, so we had studied potential in case of gravitation. Just like that, we have electric potential also. Okay, so suppose we have this charge capital Q and there is this small charge. We call it as test charge. Suppose we want to bring this from some point A to some other point B. Okay, so now there is some work done against this charge capital Q in order to bring the small charge. Okay, and now that work done will get stored as the potential energy of the system of these two charges. So that is just potential energy. Okay, work done against the electrostatic force to combine a system of charges. Okay, or to make a system of charges. It is known as the electric or electrostatic potential energy. Okay, so now how much is the work done? So suppose uh, we bring this charge from this point, so there would be some force on it. How much is the force? 1 upon 4 pi epsilon naught multiplied by q upon r square. So if it is at distance x, the force will be 1 upon 4 pi epsilon naught into q times q upon x square, right? So then in order to bring it, we have to apply an opposite force. So work done will be equal to what? Minus of f dot dx, because the force would be opposite. So for small displacement dx, work done would be minus of f dot dx, right? Then if we want to move it from A to B, so work done would be equal to what? Integral of this thing from RA to RB. Okay, and that integral comes out to be equal to what? Work done to bring from A to B, q times q, capital Q times small q divided by 4 pi epsilon naught multiplied by 1 upon RB, 1 upon final position, okay, distance of final position from the charge, minus 1 upon distance of the initial position from the charge capital Q. Okay, 1 upon RB minus 1 upon RA. So what is RB? Distance of charge Q, final distance of charge small q, okay, from capital Q, and RA is the initial distance. So this is the work done, and this much is therefore the potential energy of this system of two charges. Is this thing clear? Yes, no? All right. So we write this as the change in potential energy. So when that charge was at position A, its potential energy was suppose UA, potential energy of the system. And when you bring it at distance B, okay, at position actually, at position B, then the potential energy becomes UB. So this difference in potential energy is equal to work done. Final potential energy minus the initial potential energy is the work done. Okay. Now again, what we do is we define the potential energy at infinity equals to 0. Okay. So suppose we are bringing that charge from infinity. So what will be A? A will be infinity, right? So we are bringing it from infinity to distance r. Then A will be infinity and B is at distance r away from this charge capital Q. Okay. If you bring it from infinity to r, how much would be the work done? Work done would be 1 upon 4 pi epsilon naught multiplied by this q times q multiplied by 1 upon the final distance minus 1 upon the initial distance. Initial distance is infinity. So this thing turns out to be equal to 0, and we get potential difference, sorry, potential energy difference between what? This position r and infinity, when two charges are at distance r and when two charges are at infinity. The potential energy difference is equal to what? This thing, q times q upon 4 pi epsilon naught r. Okay, q times q upon 4 pi epsilon naught r, right? And then we define the potential energy when the two charges are at infinite distance away from each other equal to 0. This is just for convenience. So we have seen, what can we find out? We can only find out the potential energy difference, the final potential energy, okay, if minus the initial potential energy. We can just find out that the potential energy difference, right? we can't find out potential energy at a particular point. Okay, so if we define the potential energy at infinity is equal to 0, then we get this simple formula for potential energy when the two charges are separated by distance r. Okay, so that formula is what? U at r is 1 upon 4 pi epsilon naught multiplied by q times q upon r. So is this thing clear? What we can't define, we can't, I mean, what is that thing we can't find out? The exact potential energy. We can find out only the difference, and that's why for convenience we define that the potential energy at infinity is equal to 0. Okay, this is just for convenience, so that we get simple formula for potential energy when two charges are separated by distance r. Okay, and this is that formula. So then now we define the electrostatic potential due to a charge. Okay, so we know that this much is the work done to bring a charge from infinity to distance r, right? To bring charge small q from infinity and keeping it at distance r away from this capital Q. So this work done we can define in terms of potential due to this charge. Okay, how do we define the potential of this charge at distance r? Potential due to q, capital Q at r, is work done to bring some other charge from infinity to that point. Okay, and divided by that charge, the charge you brought. Okay, so potential at distance r is 1 upon 4 pi epsilon naught multiplied by q times q upon r divided by q. Q gets cancelled, and you get this simple formula for the electrostatic potential due to a charge capital Q. So because this is potential due to charge capital Q, it should depend only on capital Q. It should not depend on small q, right? So it depends only on capital Q. Okay, so this is the potential. Is this thing clear? Yes, no? All right. So then after that, this potential is a scalar quantity or a vector quantity? It's work done upon charge. So it's a scalar quantity, right? Work done is scalar, charge is scalar. So it's a scalar quantity. So this is a scalar quantity. Okay. So now if you have n number of charges, q1, q2, q3, so on and so forth, and you want to find the potential due to all these charges at this point, what will you do? You will do scalar addition, right? Because potential is a scalar quantity. So you find out potential due to first one, second one, third one, so on and so forth, and you add all those potentials to get the total potential at this point P. Okay, Q1 is at distance R1, Q2 is at distance R2, so on and so forth. So you get total potential at P is equal to V1 due to Q1, V2 due to Q2, V3 due to Q3, so on and so forth, right? So then you know potential is 1 upon 4 pi epsilon naught multiplied by q upon r. So you put that and you get this formula. Okay, so this is just process. This is nothing. Okay, here is nothing to be memorized, right? This is just a process. We need to understand this. Okay, all right. So now we found potential energy of system of two charges. Now suppose you have n number of charges. Okay, so what will be potential energy of that kind of a system? So when you bring first charge from infinity and keep it at any point in space, do you have to do some work? When you bring a charge, first charge, there is nothing in space. You are bringing first charge. Do you have to do some work? No work, because there is nobody opposing that charge, right? So when you bring first charge Q1, there is no work done. then therefore potential energy of this charge will be equal to 0. Potential energy of a single charge will be equal to 0, right? Now you bring in second charge. What will happen? So you have to do some work, and we have found it out. So there will be some work done which is equal to 1 upon 4 pi epsilon naught q1 q2 upon the distance between two charges, right, r12, and this much would be the potential energy of this system. Now suppose you bring third charge and you keep it at distance r13 from the first one, r23 from the second one. So now you have to do work against both of these charges, right? And that work done would be equal to what? Against q1, it will be 1 upon 4 pi epsilon naught multiplied by q1 times the charge you are bringing, that's q3, upon r13. And work done against q2 will be 1 upon 4 pi epsilon naught q2 times that q3 upon r23. Okay, so now in this way you can find out the potential energy of the system. So now how much would be potential energy of this system of three charges? So you add total work done. Work done in bringing q1 is 0. To bring q2 you have to do this much work done because there is already some charge q1 present. Okay, so in order to bring q2 you will have to do some work. Now you bring q3, so you have to do work against q1, you have to do work against q2. So you add all those works and you will get the potential energy of the system, right? So there is nothing difficult in this procedure. Okay, so there won't be, I mean, very few chances that there will be a question based upon this thing. Okay, so what will be potential energy of n number of charges, or at max it will be equal to n will be equal to 3 if there is a question. Okay, so now in this case we considered that there is no electric field in this region. Okay, there is no electric field in this region, so work done is just work done against the other charges. Now there can be some electric field present in the region. So when you are bringing the charges, when you bring the first charge itself, you will have to do some work, right? Because if there was nothing in space, you don't have to do a work. If there is an electric field, then you will have to do some work against the electric field, right? So how much is the work done against the electric field? So electric field is E bar. Now there will be force due to electric field. So it is just Q times the electric field, right? Force on a charge Q is equal to Q times the electric field. So now suppose you move this charge by distance dr bar. So work done would be equal to what? F1 bar dot dr bar. So F1 is force on charge Q1. Okay. So F1 is equal to what? Q1 times E bar, right? So work done to bring it from infinity to R1 is given by W1. It will be equal to integral of this work. Okay, so integral of minus q1 into E bar dot dr bar from infinity to R1, because you are keeping that charge, you are bringing it from infinity, you are keeping it at distance, sorry, at position vector R1 bar from this origin, or with respect to the origin. This thing is clear. Okay, so now this is the work done against the electric field to bring the first charge only, first charge itself. Okay, so here you have to do some work. Now when you bring the second charge, again you will have to do work against the first charge as well as the electric field, and work done against the electric field would be similar, right? So here the important point is, now we have to do work against the charges as well as the work against the electric field. So this thing is clear. Okay, so this is the procedure that we have to remember. There is no particular formula that has to be memorized. Okay, all right. So therefore the total potential energy will be what? Add up all the work done and you will get the total potential energy. So this is work done to bring these charges, okay, against the electric field. So this is for Q1, this is for Q2, this is for Q3, and this is work done against the other charges, right? So this term we got in last case also when there was no electric field. This term is new because there is an electric field, right? This thing is clear. All right. After that, important point, electrostatic potential due to a dipole. So suppose you have this dipole and you want to find out the potential due to this dipole. So now we know that dipole is system of two charges plus q and minus q separated by distance 2a. It has got dipole moment which is defined by q times 2a. Okay, this is the dipole moment, but it's a vector quantity. So what is the direction of dipole moment? It is from minus q to plus q. Okay, this is the direction, right? So electric dipole moment p bar is equal to q times 2a into p cap. So direction of p cap is from minus q to plus q. Okay. Then suppose you have a point at distance r from the center of the dipole. Okay, point is at distance r from the center of the dipole, and you want to find out the potential due to this dipole at this distance. Okay, so what will you do? Potential is a scalar quantity. You will find potential due to this one minus q. You will find potential due to plus q and you will add it up, right? So when you do that, you get some formula. Okay. So now suppose this line joining the center of dipole to the point P, it makes an angle theta with the dipole. So now see, there will be some potential due to this positive charge, potential due to negative charge. What is potential due to positive charge? It's 1 upon 4 pi epsilon naught multiplied by q upon distance of point P from the positive charge r plus. Distance of point P from negative charge is r minus. So how much would be the potential? That constant 1 upon 4 pi epsilon naught multiplied by minus q divided by this charge, sorry, this distance. Okay, so we just substitute that. Okay, and q upon 4 pi epsilon naught we can move out, and then we have to find out this 1 upon r plus minus 1 upon r minus. Okay, because these things will be common. So then we do that, all that. So this thing now it is not important. Okay, how do we get this? So the formula comes out to be equal to what? 1 upon 4 pi epsilon naught multiplied by p cos theta upon r square minus a square cos square theta. This is the complete formula. Okay, so you don't have to remember the complete formula also. There won't be any question. Okay, 99.99% there was never a question based upon total formula. Okay, and in NEET exam. Okay, so what do you have to remember? A special case that we had considered in case of dipole in electric field also. So special case is when a is very small compared to r. That means length of the dipole is very small compared to what? The distance of the point P from the center of the dipole, or from the dipole you can say. Okay, so when a is very small, this thing we can neglect. So the potential will be 1 upon 4 pi epsilon naught multiplied by p cos theta upon r square. This simple formula you have to remember. Is this thing clear? Yes, no? All right. Then point P is an equatorial point. This is a special case. So equatorial point, then this theta would be 90 degrees, right? If point P is on the equator, how much would be theta? 90 degrees, right? What is cos of 90? 0. So how much would be potential? Potential would be equal to 0. Okay. So now, in order to think that, we don't even need to do this procedure and remember the formula. Suppose you have dipole and you have any point on equator. This is the point. So potential due to minus q and plus q will be same in magnitude, because the point is at same distance from minus q and plus q. But potential due to minus q is negative, potential due to plus q is positive. So total potential gets cancelled out for any equatorial point. For all equatorial points, total potential gets cancelled out, and that's why net potential is equal to 0. Right? Potential due to minus q and plus q gets cancelled out, so net potential is equal to 0. Okay? Yes, no? Then there is case 2, when the P is an axial point, P is along the axis. Then you get again a simple formula. So when theta is 0, we know cos theta is equal to 1. So you get 1 upon 4 pi epsilon naught multiplied by P upon R square. This is the formula when point P is an axial point. Okay. So is the dipole clear? Okay. Then this was potential due to dipole. Now suppose you keep dipole in an external electric field. So we had seen in electric field that what happens when you keep a dipole like this in external electric field. So there is some force on positive charge, some force on negative charge. So these are two forces which are equal in magnitude and opposite in direction. So they make a couple. Okay, and couple exerts a torque, right? Couple rotates a body. So now this couple, due to these two forces, couple of these two forces, they rotate this body, the dipole. So they exert torque equals to what? Pe sine theta. Okay, torque is what? Pe sine theta. So now suppose you want to rotate this body, okay, the dipole, then how much would be work done? Work done would be equal to what? Just the torque exerted. Okay, you will have to exert some torque, external torque. Okay, so external torque's magnitude will be equal to P sine theta only, right? So work done to rotate it by angle d theta will be equal to this torque, external torque exerted against the torque due to electric field. Okay, multiplied by d theta. This is the work done, small work done. And if you want to rotate it from initial angle theta I to final angle theta f, then how much is the work done? So P is a constant. You just have to integrate sine theta, and integral of sine theta is what? Minus cos theta. Okay. So if you do that, so the final potential energy minus the initial potential energy turns out to be equal to minus P into cos of theta f minus cos of theta I. Okay. Or you can say theta I is theta I is theta 1, theta f is theta 2. So we will get this formula. Suppose theta I equals to theta 1 and theta f is equal to theta 2. So you get final minus initial u2 minus u1, the change in potential energy. Okay, or I will write it as delta u only. It is equal to what? It is Pe cos of theta 1 minus cos theta 2. Right? This thing is clear. All right. And then what we do is, again we define a point where the potential would be equal to 0. So which is that point? So it is when the dipole is aligned at perpendicular to electric field. Right? When dipole is aligned perpendicular to electric field, the potential we consider to be equal to 0, because cos of 90 is equal to 0. Okay. So by defining that way, we get simplified formula for u at particular theta. And what is that u at particular theta? So you get minus Pe multiplied by cos of theta. Okay, u at a particular theta is equal to minus Pe multiplied by cos of theta. So if angle between the dipole and the electric field is theta, how much is the potential energy of dipole? It is minus Pe cos of theta, or minus of P bar dot E bar, because this is magnitude of one vector, okay, magnitude of P bar, magnitude of E bar multiplied by cos of the angle between two, okay. So this is a scalar product. So for a dipole, potential energy at an angle theta with what? The external electric field is minus of P bar dot E bar, right? So this thing is clear, yes, no? Okay. So then when will this potential energy be minimum and when will it be maximum? Okay, so minimum and maximum points for this potential energy of dipole. So we know potential energy at theta is equal to minus of Pe, minus of P bar dot E bar, or you can say minus Pe cos of theta. So if cos theta is 1, then you will get u of theta equals to minus P, right? And this is the minimum, okay. So this happens when theta is equal to 0. That means the dipole and the external electric field, they are parallel to each other, okay. Dipole and the external electric field are parallel to each other. So this is for parallel case, right? So you get u is equal to what? Minus Pe. This is minimum. And if you have theta equals to 180 degrees, so I can say for anti-parallel case, theta is 180 degrees and potential energy will be equal to what? So cos of 180 is minus 1 times this negative sign is 1. So potential energy becomes maximum. Okay, so potential energy is maximum, right? So I will write this as u of 0. This is 180 means pi, so this is u of pi. Okay, so for anti-parallel case, potential energy is maximum, and for the parallel case, it is minimum. Okay. So is this thing clear, or is there a doubt in this? All right. So then our next point is equipotential surfaces. So its meaning is clear from the name itself. What is an equipotential surface? A surface where the potential would be equal at all points of that surface. Okay, so that is an equipotential surface. So now suppose you have charge capital Q. What is the equipotential surface for it? So we know potential due to this charge is 1 upon 4 pi epsilon naught into Q upon R. So which is the variable thing in this one? It is only R, right? If you change R, potential will change. If you keep R constant, potential will remain same. Okay. So which surface can you draw keeping the R constant? Here, right? Hmm. What can you draw? You can draw a sphere. Yes, no. So here is that surface, okay, for which distance of this point will be equal for all points of the surface, right? So sphere is equidistant from this charge. When it when will it be equidistant? When this point is at the center of the sphere. Okay. So this is the equipotential surface for this charge q. But is it unique? No. You change radius and you draw another sphere. That one will also be the equipotential surface. Just that potential here is suppose V1, potential here is V2. Potential will not be equal on this surface and this surface, but for all points of one surface, the potential will be equal. Got it? Yes, no? Okay. These kind of surfaces are known as equipotential surfaces, where potential at all points is equal. So now, suppose you have the electric field like this. Okay. Now, how will the equipotential surface for this electric field look like? You have uniform electric field. So here you can see the electric field line and this equipotential surface. How much is the angle between them? How much is angle between electric field and the equipotential surface? Electric field is along radius and this is a sphere. Okay. So what is angle between these two? How much is this angle everywhere? 90 degrees, right? Okay. So this is an important point to be remembered, that angle between equipotential surface and the electric field is 90 degrees. Okay. So if you have uniform electric field like this, the equipotential surfaces for that electric field will be planes perpendicular to electric field. Okay, plane perpendicular to electric field, because angle between the electric field and equipotential surface is has to be 90 degrees. Okay, so now where will be the potential greater on this surface A or B? You have two parallel surface, suppose A and B, and they are both perpendicular to electric field. That means they are equipotential surfaces for this electric field. So where will be the potential greater? Is VA equal to VB or VA greater than VB? Is VB greater than VA? Actually, I have marked it. Okay, so it is VA will be greater than VB. Okay, so how to understand this? See, now here the potential is 1 upon 4 pi epsilon naught into Q upon R. Okay, so it falls as the distance increases. Okay, so electric field is like this, and suppose you have this surface and this surface. Potential here is V1, potential here is V2. Where is it greater? On this surface, is V1 greater or V2 greater? V1 is greater. Okay. So electric field is directed from the higher potential, point at higher potential, to point at lower potential. Or electric field lines flow from higher potential to lower potential. Okay. So here the electric field lines will flow from higher potential to lower potential. So where are the electric field lines going? They are going in this direction. That means potential at A is greater compared to potential at B. Got it? Yes, no? All right. So then, okay. Now the potential difference between A and B is VA minus VB. Okay, and we define the electric field as a gradient of potential difference. Electric field is defined as change in potential, okay, minus of change in potential divided by distance, okay, minus of dV by dx. Okay, so we'll see exact formula for this. Okay, so now suppose you have a Happened network issue. So now suppose we have a linear charge like this. So how will the equipotential surface for this kind of a charge look like? It will be a cylindrical surface. Okay. You collect all the points at same distance from this linear charge or a charged wire, then these points are equipotential surface for this linear charge. Okay. So now next point is when you move a charge from, let's suppose, this point A to the point B on an equipotential surface, there is no work done. Why is work done equal to 0? Because potential is not changing. Okay, the potential is not changing, so work done will be equal to 0. Got it? Yes, no? How much would be work done? So work done to move a charge from A to B, suppose. Okay, this is an equipotential surface. So on this equipotential surface, you want to move the charge from A to B. So how much is work done? So work done to move it from A to B is equal to potential energy at B minus potential energy at A. And how can we define potential in terms of potential energy? So we know that V is equal to work done per unit charge, right? So we can move that Q on other side. So work done will be equal to what? V times Q. Okay. So it will be equal to, in terms of V, we can write it is V at B minus V at A times Q, because we are moving it from A to B. So it is final potential minus initial potential multiplied by charge. Work done is equal to final potential minus initial potential multiplied by charge. Okay. So if potential is equal, how much would be the work done? So potential difference is 0. There is no work done, right? So to move a charge on an equipotential surface, no work is done. Okay. So there are some properties of these equipotential surfaces. What are these properties? Potential at all points is 0. This is first property, or this is the definition of this equipotential surface. Then electric field lines are perpendicular to the equipotential surfaces. We discussed this. The electric field lines are directed from equipotential surface having higher potential to the equipotential surface having lower potential. We discussed this thing also. Work done to move a charge on an equipotential surface is 0. Okay. Then this is another property of the equipotential surfaces, that is the relation between an electric field and equipotential surface. So see, when we move a charge from this surface having potential A to this surface having potential B, how much is the work done? Work done is VA minus VB times Q. Okay. So work done to move it from B to A would be that much. Okay, not from A to B. So now to do this work, you will have to do some, you will need to apply some external force, because there is electric field in this region, right? Okay. You are doing this against the electric field. So external force that has to be applied is opposite to that of force exerted by electric field. So it is minus of Q times E bar, right? External force has negative sign. Force due to electric field will be Q times E bar. External force is minus of Q times E bar. Okay. So now this work done can be written as external force dot dr. Dr is the displacement. Okay. And this force is equal to minus Q times E. Okay. We are considering unidirectional case, one dimensional case. Okay. So we can write minus of QE times dr, and work done is equal to VA minus VB times Q. So we can write that this q and q gets cancelled out and we get E, the electric field, is equal to minus of Va minus Vb upon dr. Okay, and Va minus Vb can be written as dV. dV means change in potential. Okay, so now electric field can be written as minus of dV by dr. Okay, so this is called as potential gradient. What is gradient? Change in a quantity with respect to distance is known as gradient. So this is the potential gradient. Change in potential with respect to distance is potential gradient. Okay, change in a quantity with respect to distance is gradient of that quantity. So this is change in potential. That's why this will be called as potential gradient. So we have electric field equal to minus of potential gradient, or minus of, you can say, derivative of potential with respect to r. Is this in clear? Okay. So now we considered a one-dimensional case, but is the electric field one-dimensional? Electric field, is it a scalar quantity, or sorry, not scalar quantity? You have electric field in space. How many components will it have? It's a vector quantity. Yeah, 3 components, right? So for one-dimensional case, suppose you have only x-axis, only y-axis, or z-axis, you will have this formula. Okay, but for a three-dimensional case, what will you have to do is you have to consider all 3 components of the electric field. That means now x component will be given by derivative of potential with respect to x. Okay, y component will be given by derivative of potential with respect to y. Z component will be given by derivative of potential with respect to z. Okay, but you can see I have written these derivatives in slightly different manner. So what is that slightly different manner? This is called as partial derivative. This is known as partial derivative. Partial means what? You will consider y and z as constants when you take derivative with respect to x. So this is the partial derivative with respect to x. What is partial derivative? So partial derivative with respect to x means when you treat the other two variables y and z as constants. Okay, partial derivative with respect to y means there will be x and z in the formula of v, those you will treat as constant. Okay, partial derivative with respect to z is when you treat um, x and y as constants and you take derivative with respect to z. Got it? Yes, no? All right. So now this thing can be written in a simple form, like E bar is equal to this thing, okay, minus of derivative with respect, partial derivative with respect to x. So this is called as dou v by dou x, okay, or this is also called as del v by del x. So I generally call it del v by del x. So del v by del x times I cap plus del v by del y times j cap plus del v by del z times k cap. Okay, that is E bar. So this can be written in a simple form. So this is known as Dale operator. Okay, this is known as Dale operator, or it is also known as gradient operator. Okay, so this thing del by del x times I cap plus del by del y times j cap plus del by del z times k cap. Okay, so this is equal to, Dale operator is equal to this thing. So when you write E bar is equal to minus of Dale operator acting on V, means that you multiply V with this thing. So you will get ultimately this thing only. You got this? Yes, no? Okay. So now this can be understood well if you have an example. So for an example, suppose you have this function V, the potential in space is suppose xyz. Okay, potential is what? Xyz. Then how much would be the electric field? So we know electric field is equal to what? It is minus of del v by del x times I cap plus del v by del y times j cap plus del v by del z times k cap. okay, and you want to find it electric field at 111. Okay, this is the point. So that's okay. So now see, you will put V equals to XYZ here, here as well as here. So V is equal to XYZ. Okay, you have put it. Then you are taking derivative with respect to X. So what is constant? When you take partial derivative with respect to X, Y and Z will be treated as constants. So whatever terms you have containing y and z, it may be y, it may be y square, it may be sine y, e raised to y. Okay. Similarly for z, you will take them outside of the derivative because it's a constant. So you have taken it outside of the derivative, and then simply you have to take derivative with respect to x of the terms containing x. Okay, or the function of x. So here you have simply x only. So dx by sorry, del x by del x is just equal to 1. It's just like ordinary derivative. Okay, so this is 1. When you are taking derivative with respect to y, you will treat x and z as constants. You will take them outside. Okay, then what remains? Only y. So you have derivative of y with respect to y. That is also 1. Okay, this is also 1. Then here you have xyz derivative with respect to z. So you will treat x and y as constants, okay, because you are taking partial derivative with respect to z. So x and y out, you have dou z by dou z, okay, or del z by del z. So that is also equal to 1, right? So then what remains? Minus of yz into I cap, because this thing is 1, okay. Partial derivative of x with respect to x is 1, partial derivative of y with respect to y is 1, partial derivative of z with respect to z is also 1. We have minus yz times I cap plus xz times j cap plus xy times k cap, right? So this is your electric field. This is the formula. Now you can put any point. So this is point 111, means x is 1, y is 1, z is 1. So now you got the formula for electric field. You can put any point, okay, whatever point you like. So our point is 111. So that means it is y is 1, z is 1. Okay. So this is 1 I cap. X is 1, z is 1. Okay. So 1 j cap. And x is 1, y is 1. So 1 k cap. So minus of I cap plus j cap plus k cap, or minus of x cap plus y cap plus how did I write this? I wrote first two in terms of x and y, and last one in terms of k. Okay, sorry. So I cap plus j cap plus k cap, right? This would be the electric field. Is it clear? All right. So now we'll see some problems based upon these things. We'll see some simple problems. So a conducting sphere of radius r is given a charge q. The the electric potential. I just taught equipotential. So equipotential is coming to my mouth. Okay. So the electric potential and the electric field at the center of the sphere respectively are. Tell me. You have conducting sphere of radius r. Okay. All right. So you can think it in this way. How much is the electric field inside this conducting sphere? It is 0. Okay. Then how much would be potential difference between this point and this point? E is 0, dV is 0. That means potential difference is 0. right? Potential difference between this point and this point is 0, right? Okay. So electric field is 0. Now how much is potential? So we know, so suppose you take any internal point, okay? So they are asking at the center. So charge on this sphere is capital Q. So how much is distance of this point from this charge? It is R, right? So if you take some small charge here, how much would be potential due to that small charge? Let's call it dq. So I can say dv 1 upon 4 pi epsilon naught, or say k times dq by r. Okay, that is potential due to this small charge. Now you want to find out potential due to the sphere at the center. How much will be that potential? It will be integral. Okay, I took dv for this and I am taking dv for potential difference also. Okay, so I will say v because of dq, okay, is this much, right? So how much would be the total potential? So potential because of the total charge q will be equal to what? Integral of this. Okay, so k you can take out. R is a constant because each and every charge or each and every small charge element is at same distance from this point, the center, and therefore R is also constant. So how much is integral of dq? Just q, right? So it is potential at the center would be k upon, that is 1 upon 4 pi epsilon naught multiplied by integral of dq is just q upon r. Got it? Yes, no? So now you have to remember this formula, that potential due to a charged spherical shell at the center is 1 upon 4 pi epsilon naught q upon r. Okay, but now see the electric field, we know it is equal to 0. And how do we write the electric field? It is minus of dv by dr. We just saw this. So it is minus of change in potential with respect to distance. So potential at the center is, it is how much? 1 upon 4 pi epsilon naught q by r. You take any other point, if there is potential difference, there would be electric field, right? Electric field is what? Minus, forget about the minus sign. It is potential difference divided by distance, right? So if there is potential difference, there will be electric field. Electric field is 0, we know. That means potential difference cannot be there. Potential difference will be 0. And if potential difference is 0, that means potential at each and every point is same, right? How much is that? 1 upon 4 pi epsilon naught into q upon r is the potential at each and every point, for each and every internal point of this spherical shell. On the shell also it will have same value, and after that it will fall as r. Okay, this thing is clear. What is the answer of this question? The electric potential and electric field? Option B, right? Okay. Let us see next one. A bullet of mass 2 gram is having a charge of 2 microcoulomb. Through what potential difference must it be accelerated starting from rest to acquire a speed of 10 meters per second? Tell me. bullet of mass 2 gram having charge 2 microcoulomb. It has got some charge. By what potential difference must it be accelerated starting from rest to acquire a speed of 10 meters per second? You see, this is a charge Q and there is some potential difference. Okay, that means there is some electric field. Okay, so this charge is pushed by this electric field. What will happen? It will get accelerated, right? Initially, its speed is 0. Charge is pushed. That means electric field exerts a force. Okay. So how much is the work done in this case? So work done is equal to suppose initial potential is A, final potential is B. Okay. Sorry, initial point is A, final point is B. So VB minus VA is the potential difference multiplied by charge. This is the work done. And this work done, what will happen? So this is the force, sorry, this is the work done because of the force exerted by electric field. Okay, right. So now this work done gets stored as the kinetic energy. So where is kinetic energy coming from? Work done by the electric field or work done by the potential difference, right? Got it? Yes, no? Okay, so this is equal to half of mv square. And you want what? You want potential difference. So take q on other side. Okay, so VB minus VA, or you can say delta V, is equal to half mv square upon q. And now we just have to put the values. Okay, what's that? So this is equal to half of m is 2 grams, 2 multiplied by 10 raised to minus 3 multiplied by, in denominator charge is 2 microcoulomb, so 2 times 10 raised to minus 6, and speed is 10 meters per second. So this is 100. V square is 100. Okay, so 2 gets cancelled out, still you have this 2. Okay, so 100 divided by 2 is 50, right? You have 50, and this 10 raised to minus 3, this goes to numerator, 10 raised to minus 6, it becomes plus 6, plus 6 minus 3 is plus 3, so it is 10 raised to 3. That many volts is the potential difference. Okay, so did I tell you the unit of potential? No, but we know this from 10th standard, etc., right? The unit of potential is what? Volt. Work done per unit charge. Okay, the unit is volt. All right. So this thing is clear. What is the answer then? 50 kilovolt. Yes, no? Any confusion in this? Okay, good. Let's see next one. Now, electric potential at a point in free space due to charge Q, coulomb, is Q multiplied by 10 raised to 11 volts. The electric field at that point is. So what's the relation? For a charge Q, okay, electric field is 1 upon 4 pi epsilon naught times Q upon R. Yeah, R square, R square, R square. And electric potential is what? 1 upon 4 pi epsilon naught Q divided by R. Okay. So then E is equal to V divided by R. Right. So electric field you want, so it is equal to V upon R for a charge. So now what was given at a point in free space due to a charge Q? Okay, electric field is given. It is this much. Q multiplied by 10 raised to 11. Okay. It is q multiplied by 10 raised to 11. This is given. And you want, sorry, electric potential is given and you want the electric field, right? So given the potential, we can find out R because we want electric field. How much is potential? Q into 10 raised to 11. It is equal to 1 upon 4 pi epsilon naught times Q by R, right? And all options are in terms of epsilon naught, epsilon naught. So let's keep R in terms of epsilon naught. Okay. So if you take that R on that side, R on the other side, right? So you will get 1 upon 4 pi epsilon naught multiplied by 10 raised to minus 11. Okay. R will be equal to what? 1 upon 4 pi epsilon naught multiplied by 10 raised to minus 11. So E is equal to V upon R, right? So value of V is known, Q into 10 raised to 11. And how much is R? 1 upon 4 pi epsilon naught multiplied by 10 raised to minus 11. Take minus 11 to numerator, it becomes plus 11. So that's 22. 4 pi epsilon naught to numerator. Okay, so it is 4 pi epsilon naught q multiplied by 10 raised to 22. This is the answer. Okay, but there is nothing in this one, right? Because one thing is given, other thing we have to find out, right? So this is just, okay, nothing, like sleight of hand, you can say. So what is the answer? Option C. Okay, let's see next one. As per the diagram, a point charge q is placed at the origin O. Work done in taking another point charge minus q from point A, this is point A, coordinates 0, A, to another point B along the straight path AB is, okay, and coordinates of B are A0. So tell me how much would be the work done? Point charge plus q is placed at origin. So here you have a charge plus q and you move another charge minus q from A to B. Minus q is moved from A. A is the initial point, B is the final point. How much would be the work done? It is the potential. Potential, sorry, work done will be equal to what? Work done to move it from A to B is equal to potential at B minus potential at A into the charge that you are moving minus q. Okay. So how much is potential due to this? You can take k outside. K and q also we can move outside, right? 1 upon this distance, okay, OA minus, sorry, it was B first, right? So 1 upon OB minus 1 upon OA times minus q. So how much is OB? What are the coordinates of this point? A0. So how much is this distance? This is x coordinate A, right? This distance is A. How much is OA? It is also A. So this is A, this is also A. That means this thing is 0. Okay. So instead of doing this, what we could do is, see, this charge, okay, we could start like this. So point A is at distance A from this charge. Point B is also at distance A. That means potential due to this one at A and B is same. So there is no potential difference. Therefore, you keep this another charge here or here, it does not matter. There will be no work done, right? So work done is equal to 0. This is clear? All right, good. Next one, a short electric dipole has dipole moment of this thing. The electric potential due to the dipole at a point at distance 0.6 meter from the center of dipole situated on a line making an angle 60 degree with the dipole axis is. So they are saying use the formula, and V is equal to, no, you don't want the potential energy, you want electric potential due to the dipole. 1 by 4 pi epsilon naught P cos theta upon, okay, x square you say, or r square, right? Same thing. So 1 by 4 pi epsilon naught is 9 into 10 raised to 9. P is given, is the P, yeah, 16 into 10 raised to minus 9. It is cos of which angle? 60 degree. Cos of 60, yeah, half. And what is distance is 0.6. So this will, r square will be 0.36, right? Or I will write this as, it's better to write in terms of 10 raised to some power. Okay, so 36 into 10 raised to minus 2. Why? Because we can move the powers easily. Okay, so then we have 9 fours are 36, 4 fours are 16, 10 raised to plus 9 minus 9 gets cancelled out. Okay, this 10 raised to minus 2 goes to the numerator plus 2. So 400 multiplied by cos 60 is half. 2 into 10 raised to 2, 200. Okay, so option B, right? So this is asked by NTA, NEET 2020 means asked by NTA, and very simple. Okay, actually, in fact, all questions till now were simple only. Next one, 4 point charges minus q, 2q, 2q are placed one at each corner of the square. The relation between q and q for which the potential at the center of the square is 0 is, tell me, what will we do? Potential at the center is 0. So let's draw a square. All right, so this is one charge is minus q. After that, you have minus small q, then 2q and 2q. Okay, maybe 2q here and 2q. And at center, the potential is 0. So how much is relation? What is the relation between capital Q and small q? So can you say that center is at same distance from all the charges? Okay, because all charges are at the four corners of a square. Okay, so distance of square center would be same. So how much is total potential at center? Total potential at O, sum of potential due to all charges. K multiplied by, K will be common, minus Q by R, okay, plus minus Q by R plus 2Q by R plus 2 capital Q by R, right? So this is, then R also we can take common. So potential is 0, so this thing is equal to 0. Okay, R also we can move outside, K by R times this thing. What? 2q minus q is q, and 2q, Small 2q minus a small q is also small q, a small q. So this thing also we can move outside. I mean, we can take it on other side. So this will go in multiplication with 0. So that will become 0. K divides 0. So again, it remains 0. So q plus q is 0. That means q is equal to minus of q. Okay. So this is another simple problem. Let's see next one. Looks similar. 4 charges plus q minus q are placed at the corners of a square of side 2l. The side is 2l. Okay. Then now electric potential at A, at this A, midway between the two charges plus q and plus q is, what is the electric potential here? This is the question. Okay, just a second. So we just have to add the potential due to all of them, right? So these two are at same distance. This total distance is 2l. This much distance will be l. Okay, potential due to this and this. What's that? V will be equal to 1 upon 4 pi epsilon naught. We can take common q upon L plus q upon L, right? They are at same distance, L. Okay. What about this minus q and minus q? Their distance is not same. So this is the distance, right? How can you find it out? Right, L square plus 2L. Right, this is 2L, this is L. Okay, so if you call this distance as R, so you can say R square is equal to L square plus 2L square. Okay, so that is L square plus 4L square, 5L square is R square. R is equal to root of 5L. So you have plus minus Q divided by this distance, which is root 5L, plus minus Q upon root 5L. Okay. So again, this is Q plus Q, 2Q. This is minus Q plus minus Q, minus 2Q. So you can move that 2 also outside, I guess. Q also outside. So 1 upon 4 pi epsilon naught. You can move 2Q upon L outside. From here, 1 will remain. And from here, it will be minus 1 upon root 5. This is the answer. Okay, it's option C, right? See, this one was also simple. Okay. Next one, 3 charges, each plus q, are placed at the corners of isosceles triangle ABC of sides BC and AC. So BC and AC are same. Okay. Okay, they mean BC and AC are, they have same length. Okay, 2a, and that length is also given. It is 2a. BC and AC length is 2a. D and E are midpoints of BC and CA. D and E are midpoints. Okay. Work done in taking a charge Q from D to E is, from D to E. How much work will be done? Tell me. So here you have 3 charges. Here you have 1 charge. Here you have second charge and third charge here. So tell me. Okay. So how much would be work done? You can start with this. Work done to move it from D to E. It's potential at E minus potential at D. right? Multiplied by charge. Sorry. Potential at E minus potential at D multiplied by whatever charge you move. So what is potential at E? So it is potential due to this charge, and this charge. Okay. So because of this and this, it is Q upon A and Q upon A. You can move, take constant K. Potential at E is Q upon A plus Q upon A due to this charge and this charge, right? Because this total distance is 2A. And suppose this distance is R, this distance is R, okay? Distance B, you can say. So potential due to this one will be plus Q upon BE. This is total potential at E. Minus, what about point D? So due to this one and this one, potential at D will be Q upon A plus Q upon A, right? Due to this one and this one, okay? Plus you have, due to this charge, it is Q upon AD, right? So now this thing gets cancelled out, and you have Q upon BE minus Q upon AD. So is this distance and this distance equal? What can you say? Yes, no, they are equal, right? Because, yeah, because this is an isosceles triangle. This side and this side is same, okay? This is the midpoint. If this is a midpoint, that means you are drawing this line, okay, which bisects this line, okay? You are drawing a line from this point which bisects this line. So what is this thing? It's a perpendicular bisector, right? This one will also be a perpendicular bisector, okay? So if this is a perpendicular bisector of this side, this is a perpendicular bisector of this side, you can find it out, okay? Because this length and this length is equal, okay? How much would be length of this one? So you can take this as what is this triangle, right angle triangle, right? So this side square will be equal to this side square plus this side square, but this side is 2A, this side is A, okay? So BE square, I can say, is equal to BC square minus EC square, that is equal to 2A square minus A square, okay? 3E square, sorry, 3A square, got it? Similarly, you have, that is BE square, AD square will be equal to, AD square will be equal to what? This side square minus this side square, okay? If I join AD, so I have to consider this triangle. It will be this side square minus this side square by Pythagoras theorem. So it is also, okay, AC square minus what? DC square. So that is also 3A square. That means AD is equal to BE. AD is equal to BE. Okay, so if AD is equal to BE, that means this term is also 0, right? So work done is equal to 0. This is the answer. Okay, and this thing I have explained in very detail. Actually, it shouldn't take much time. This is an isosceles triangle. Okay. So now, whenever you are moving a charge from one point to another point, you should think how much is potential at this, how much is potential at this. So, potential at this, there are these two charges, right? So, potential due to this one and this one, okay, will be what, Q upon A, Q upon A. What about this? So for this, potential due to this one and this one is Q upon A, Q upon A. Okay, these are two contributions. Then there is another charge. You have this charge. So potential due to this charge is Q upon this distance. Potential due to this charge here is Q upon this distance. Those distances are also same. So that means potential at those points are equal. That means when you move the charge from one to other, the work done is zero, right? Okay. So I have told this these statements now in terms of few statements. It didn't take 1 minute. Okay, so just thinking this and marking shouldn't take like 1 minute. Okay, should take much lesser time. All right, so this will come with practice only. Anyway, so this is clear. Okay, next one, charges plus q and minus q are placed at points A and B respectively, which are distance 2l apart. C is midpoint between A and B. The work done in moving charge plus Q along semicircle CRD is. Okay, so tell me how much would be the work done? You are moving it. Okay, don't think about the path or work done for all paths is same. Okay, so suppose you are moving a charge from point A to B. How much is the work done? Work done is VB minus VA times Q. You move it like this, you move it like this, you move it like this, doesn't matter. Path do not matter. Okay, work done along any path would be equal, right? So paths do not matter for electrostatic force, paths do not matter for gravitational force also. Okay, so then if paths do not matter, how much is the work done? It is potential at D minus potential at C multiplied by the charge. What are you moving? Charge capital Q. So potential is there. So take 1 upon 4 pi epsilon naught outside because there is epsilon naught, epsilon naught. Okay, in all questions. How much is potential at D? So there are two charges. What are those two charges? Plus Q and minus Q. Where are they kept? At A and B. So this is plus Q. At B there is minus Q. And how much is potential due to them at D? So you can say, okay, how much is this distance? 2L. Okay, this is midpoint and this is semicircle. That means this distance is also L. So how much are these distances? L, L and L. Okay. So potential at D due to this one is how much? Q upon 3L, right? Due to this one, L, L, L. How much is distance of this point? 3L. So potential is Q upon 3L. Potential due to minus Q is minus Q upon what? L. Okay, that's potential at D minus potential at C. So for point C, it is at same distance from plus Q and minus Q. So it is Q upon L minus Q upon L. Okay, plus minus Q upon L, right? Times capital Q. Okay, so actually this point has potential equal to 0, right? Plus Q by L minus Q by L. So then you just have to find out this thing. What is this? Q by 3L minus Q upon L. So this is 3Q by 3L. Okay, so Q minus 3Q is minus 2Q. So the answer is This is equal to 1 upon 4 pi epsilon naught times q multiplied by minus 2 by 3. Okay, minus is there in only one option, option C. This is okay, is it? Yeah, 2 and this is 4. So 4 by 2 will give you 2. 2 times 3 is 6. Okay, so this is equal to minus of q upon, okay, 6 pi epsilon naught, and yeah, that's L was also there. So this is the answer, option C. This is clear? Okay, very fast. All right. So this was also very simple. Again, this is a similar question. Two charges Q1 and Q2 are placed 30 centimeter apart. Okay, Q1 and Q2. Then a third charge Q3 is moved along arc of circle of radius 40 centimeter from C to D. You move it from C to D. The change in potential energy of the system is, how much is the change in potential energy? Okay, so we can think of this way, potential due to Q1 at C and D remains same, right? So I can say potential due to Q1 at C and D is equal. So when you move this charge, will there be any work done against Q1? There's no, there is no work done against Q1 because potential of Q1 at this point and potential of Q1 at this point is equal. There is no work done against Q1. Not it, yes, no. Okay. So there is no work done against Q1. No work is done against Q1. Okay. Against Q1. In last problem also we could say potential due to this charge minus Q at C and D is equal. There is no work done against minus Q. So there is only work done against plus Q. If we had found that work done against plus Q also, we could have got the answer, same answer. Okay. So in this one, now how much would be the change in potential energy? So change in potential energy, delta P, is work done against other charge, which is the other charge, Q2. How much is that? So potential of Q2 at the final point, okay. So let's take 1 upon 4 pi epsilon naught multiplied by what? Q2 divided by distance BD minus potential of it at initial point, that is Q2 divided by, oh, initial point is this one, right? So it is BC. And what charge are you moving? This is the potential difference. You are moving Q3. Okay. So then what do they say? That it is this many times the change in potential energy is this many times of K. What is K? This is the question. So what is this thing? Q3 upon 4 pi epsilon naught. Q3 upon 4 pi epsilon naught. Okay. All right. So can you tell me how much is this distance? Okay. Okay. So what will be that? What will that be? I or 50? 50, no? Okay. All right. So I'm just making some space. So this can be written as, okay, delta P. They have said that it is Q3 upon 4 pi epsilon naught times K is equal to this thing. Q3 divided by 4 pi epsilon naught multiplied by, what do we have? Q2 we can take common. 1 upon BD is 1 upon BD is what? This is 40. Okay, so this much distance is 10, right? Yes, no, minus 1 by 50. But these are in centimeters. Okay, so we can say this is 1 upon zero point 0.1 in meters, and this is zero point 0.5 in meters. Sorry, not minus. This thing is clear, yes, no? Or let me write it like this. So it is Q2, okay, this thing multiplied by Q2 multiplied by what? I will write this as 10 centimeter. It is 10 into 10 raised to minus 2. You can move that minus 2 in numerator, minus, this is 50 into 10 raised to minus 2. Okay, we can move that in numerator. So this is 100, this is 100, 100 by 10 is 10, 100 by 50 is 2. Okay, so 10 minus 2 is 8. So K is equal to what? Therefore you get K equals to 8 times Q2. This is the answer, because this thing gets cancelled out. Got it? Yes, no? Is there a confusion in this one? Okay, sure. Clear, no? Is there a question in this? Yes. Good. Then let's see next one. Identical charges minus q are placed at each corners of a cube of side B. Then the electrostatic potential energy of charge plus q, which is placed at the center of cube, will be. Okay. So again, this is simple. How much will be the electrostatic potential energy of charge plus q? You have two charges, sorry, you have four charges at four corners. Not four charges, it's a cube. I thought it's a square. Okay, so this is a cube, side B. Okay, so this is a cube. Oh, all right. And this side is B, right? And you want the potential energy of this charge, which charge capital Q, which is placed at the center of the cube. So tell me. Okay. So is the charge at same distance from all of the charges, all the other charges? There are charges. Which are the charges? Minus q, minus q, minus q. Sorry. Minus q, minus q, minus q, minus q, minus q at all corners. And you have, okay, charges at all corners and one charge at the center. Is its distance from all charges equal? It is equal, right? So how much is that distance? Hmm. Distance of this charge we have to find out. Okay. So see, I have drawn a diagonal here. This is the diagonal. Okay. And then I am drawing a perpendicular from this charge on the diagonal. So this is at the center. That means it is at this much height. Okay, it is at this much height. So if the total height is equal to b, how much is this height? Height of the center? It is b by 2, right? So this distance is b by 2. Okay, this much distance is b by 2. What about this distance? How can you find it out? So you can say this is diagonal. So b square plus b square will be equal to this distance square, right? Let's call it root 2b. Very good. So this distance will be equal to what? Let's call it something. So this is a, b, c, d. So distance AC is equal to root 2 times b. Distance CD is equal to what? B by 2. And we want this distance AD, because distance of all charges from this charge will be equal to this much distance. Okay. So this distance AD square will be equal to root 2b square or AC square plus CD square. So tell me. It will be half of that. Yeah, very good. A to B is root 2b. So A to C will be B upon root 2. Sorry, not, yeah, half of that, half of root 2b, that is B upon root 2. Okay, yeah, good. All right, so this is, take square of this. So this will be B square upon 2 plus B square by 4. Okay, so that is 3b square divided by, right, 3b square divided by 4. 4. Okay, so AD will be equal to then root 3 B by 2. Right, this thing is clear. So total potential at the center, let's call the point D, okay, will be equal to, point D is the center, 8 times of, we have 1 upon 4 pi epsilon naught, yeah, 4 pi epsilon naught is there, multiplied by what? The charge minus q upon distance AD, because this charge is at same distance, center is at same distance from all the charges. So that thing will be the total potential. Okay, potential due to one charge multiplied by number of charges is 8. Okay, and AD is equal to root 3b by 2. Okay, so that 2 can go to the numerator. 2 will move to the numerator. Okay, 8 by 4 is 2. 2 times that 2 is 4. So we have 4 upon minus 4q upon pi epsilon naught, right, times the root 3b. You got it? This will be the potential. And we want the electrostatic potential energy. So electrostatic potential energy is equal to what? This potential due to all the charges at this point multiplied by the charge that you are, suppose you are bringing it from infinity and keeping at that point. So multiplied by that charge. So potential energy will be Vd multiplied by the charge that you are keeping. So minus q time, okay, I wrote extra 4 here. Okay, so it will be minus 4q times q minus 4q square upon root 3 pi epsilon naught b. That would be the answer. So minus 4q square upon root 3 pi epsilon naught b. Option C. So this is slightly lengthy question, right? You have to think about these things and then you have to solve. But question is simple. Okay. Let us see next one. In bringing an electron towards another electron, the electrostatic potential energy of the system becomes zero, increases, decreases, remains same. I like questions like this. Tell me. Increases. See, now when you have two electrons, this electron will repel the other electron, and you are doing the work against this repulsion. That means you have to put some energy, right? So when you are putting energy in the system, the energy of the system increases, right? So if it was a proton and you have an electron, so proton is already attracting it. Now if you want to move it close, don't have to do uh, work against that system, right? So in that case, the potential energy will decrease. Okay, this is clear. Next one, there is electric field E in x direction. The work done on moving the charge 0.2 coulomb through a distance 2 meter along a line making angle 60° with x-axis is 4 joule. What is the value of E? Okay, so this is very simple. There is an electric field in x direction. Okay, work is done to move charge 2 coulomb, 0.2 coulomb through a distance of 2 meter along a line making an angle 60°. Okay, is 4 joule. So you are moving the charge along this line. Electric field is like this. Okay, so this is suppose Q moved by 2 meters. So how much is work done against the field? Work done will be equal to what? F bar dot dr bar, we can say. Okay, that is F into dr multiplied by cos theta. Theta is 60°, right? It is 60°. Okay, and F is equal to what? So electric field is given. I mean electric field we want to find out. So F is equal to Q times E. So work done is Q into E multiplied by dr into cos theta, cos of 60. Okay, so now E we want to find out. We can move Q dr and cos 60 on other side. So we get E equals to work done divided by Q dr. Cos 60 is half, right? So everything is given. Work done is what? 4 joule. Q is what? Minus 2, sorry, 0.2. dr is what? 2, and this is half. So this 2 gets cancelled. 4 divided by 0.2. 4 upon 2 would be 2. 4 upon 0.2 would be 20. Okay. So answer is 20 Newton per coulomb. Okay, so this is also very simple. Next one, a charged particle Q is shot with speed v towards another fixed charged particle capital Q. It approaches Q up to a closest distance r and then returns. If Q were given speed 2v, the closest distance of approach would be. Tell me. First it is given speed v. Okay, this charge is given speed v, so it goes till distance what? It is given, it goes till distance r. Okay, and stops. So what happens? This kinetic energy gets converted to potential energy. Yes, no? Okay, its kinetic energy gets converted to potential energy. and it goes till distance r and stops. Okay, so at that point kinetic energy will be equal to 0, but potential energy will be equal to what? Q times q, k multiplied by q times q upon the distance. Okay, distance is r. Now you are increasing the kinetic energy, so it will go closer, because in order to go closer to that another charge, you have to do some work. Okay, you have more energy, you will do more work, right? How close we have to find out. Okay, so we can say initial kinetic energy, k1 will be equal to potential energy in first case. Okay, so I can say initial ke gets converted to ke at initial point is potential energy at final point. Okay, so for first case the kinetic energy is, let's call it E1, will be equal to what? Potential energy U1, and E2 will be equal to potential energy U2. You can take, you can divide these two. Okay, so what do you get? So what is kinetic energy? Okay, you got up to this point. Is it clear till this point? Yes, no? So what is kinetic energy? It's half of mv square. So initially it will be, in first case it is half of mv square. In second case it is half of m into 2v square. In first case the potential energy is k multiplied by q times q upon r. You can call that r1. Second case it is k into q times q upon, call it r dash or r2, and that r2 we have to find out. So this half m gets cancelled. Then v square gets cancelled. You have 1 by 4 on left hand side, and on right hand side that q k q q k q q gets cancelled out. This r goes to denominator. This is in denominator of denominator. So this one goes to the numerator. It is r2 by r. Okay, so move that r on other side. You get r2 equals to r by 4. Okay, so the answer is r by 4. This thing is clear? Yes or no? All right. Then let's see next one. Which of the following is not true? For a point charge, the electrostatic potential varies as 1 by r. For a dipole, the potential depends on position vector and dipole moment vector. The electric dipole potential varies as 1 by r at large distance. For a point charge, the electrostatic field varies as 1 by r square. Tell me. For a dipole at large distances, what happens? The potential falls as, formula is V is equal to K into P cos theta divided by x square, okay, or r square. So it is inversely proportional to distance square, and they are saying it's inversely proportional to r, which is definitely not true. Okay, very good. So it is option C. Right, let's see next one. In the region of space with volume 0.2 meter cube, the electric potential is found to be 5 volt throughout. Okay, everywhere the potential is 5 volt. The magnitude of electric field in that region is. So the electric field is equal to what? Minus of dV by dr. If V is constant throughout, What will be electric field? What is derivative of a constant? Yes, derivative of a constant is 0, right? Derivative of a constant is 0. So electric field is 0. Okay, so this is very, very simple. Okay, if potential is constant, electric field is 0. Okay, okay. So then, all right, this will take time, or I don't know. Let's see. Two metal spheres, one of radius r, other of radius 2r, respectively, have same surface charge density sigma. Okay, two metal spheres, they have same surface charge density sigma. They are brought in contact and separated. What will be new surface charge densities on them? Okay, so you have two metal spheres. Initially, they have same surface charge density and their radius is r and 2r. Okay. So here, now what will happen? So we know that potential is equal to what? For a sphere, potential will be equal to 1 upon 4 pi epsilon naught multiplied by q upon r. Right? Mhm. Okay. So now suppose this r is okay. This r is external point. This will be the formula 1 upon 4 pi epsilon naught into q upon r. Now can we write q in terms of sigma? Can we write q in terms of sigma? Sigma is what? Q upon area, that is 4 pi r square. So q is equal to sigma times 4 pi r square. So you put that here, what do you get? You get formula for potential in terms of sigma. Okay, that will be 4 pi r square upon 4 pi epsilon naught into r. So now this 4 pi gets cancelled out. Okay, and you have, oh, I didn't write sigma, it will be sigma r square upon epsilon naught r. So see, tell me. Mm. Where? No, I will explain. Wait, wait. So suppose this is your okay sphere, okay, spherical shell, hollow spherical shell, right? So its radius is r, and the distance at which you want to find out the potential is suppose okay this distance from the center is r. Okay, so the formula is this formula we know 1 upon 4 pi epsilon naught into q upon r, right? This formula we know. Okay, then I want to find out the potential in terms of sigma. So for that I have written q in terms of sigma. Okay, so this much distance is r. So you get v equals to, so now what I will do is I will copy this question on the next page. Okay, and let's see this point, potential due to a charged sphere in terms of surface charge density in terms of sigma. Okay, this is our charged sphere and we want to find out the potential in terms of sigma, right? Charge is q, radius is capital R, distance of point P where we want to find out this potential is small r. Okay, So now, see, we are getting this formula. Okay. So V is equal to what? V is equal to sigma r square upon epsilon naught r. Okay, this will be general formula. Okay, this thing we have to remember. This thing we have to remember, sigma r square upon epsilon naught small r. And V at r. Okay, that means on the surface, I will say, on the surface itself, this r will be equal to capital R, right? If I want to find potential on the surface, small r is equal to capital R. So what do I get? V will be equal to what? Sigma times r divided by epsilon naught. Sorry, sigma times r only upon epsilon naught. This thing is clear. Okay. Please remember this formula. And what will be potential inside of the sphere or spherical shell? No, potential we saw in first question itself. We started with this, that electric field is zero. So if electric field is zero means potential remains constant. Potential remains constant means whatever potential is there on the surface, same potential is inside, right? So potential inside and on the surface is given by sigma r upon epsilon naught. Potential outside will be given by sigma r square, capital R square. Capital R is radius, okay, divided by epsilon naught small r. Okay, this thing is clear. All right. So now we have two metal spheres, one of radius capital R, another one of 2r respectively, have same surface charge density sigma. Okay, so one has radius small r, sorry, capital R, other one has 2 times r, but the surface charge density is equal. Okay, r and 2r. So now you are bringing and keeping them in contact with each other. What will happen? So there is some potential of V1, some potential of V2. Where will the charge flow? From higher to lower potential, right? Yes, no. Charge will flow from higher potential to lower potential, right? Okay. Till what time will it flow? Till the time potentials become equal. So finally, what will happen? Okay, charges will flow from V1 to V2, because if surface charge density is equal, then see, potential is sigma times r upon epsilon naught. Okay, surface charge density is equal, so potential of second one will be greater. So V2 to V1. Right, potential on the surface is sigma times r radius upon epsilon naught. So V2 will be greater. So charge will flow from V2 to V1 till V1 becomes equal to 2. Okay, that means now final sigma 1. There will be some relation between final sigma 1 and final sigma 2. So surface charge density of first one becomes sigma 1. For second one, it becomes sigma 2. So we can say sigma 1 times R1 upon epsilon naught. Okay, this is our formula, right? We just found it. Sigma times, what is potential on the surface? Sigma times R upon epsilon naught. So sigma 1 times R1 upon epsilon naught is equal to sigma 2 times R2 divided by epsilon naught. Epsilon naught gets cancelled. Okay. So what is relation between sigma 1 and sigma 2? So R2 is equal to what? 2 times of R1. Okay. So we can say, we can take the 2 on this side. So sigma 1 will be equal to 2 times sigma 2. Okay, or we can say sigma 2 will be sigma 1 divided by 2. So which is the answer? Can we figure out answer from this thing? This is 5 by 6, this is 5 by 2. So definitely not. Okay, 5 by 6 times 2 will be how much? 5 by 3, right? So this is not correct. This is 5 by 2, 5 by 6. Okay, 5 by 2 times sigma, this is 5 by 6 times sigma. So this is also not correct. This is 5 by 2 times sigma, this is 5 by 3 times sigma. So this is also not correct. So it is option B then, if 3 are not correct. Okay, but let's check this one also. So sigma 1 is 5 by 3 times sigma, sigma 2 is 5 by 6 times sigma. Okay, that means sigma 1 is 2 times of sigma 2, right? So this is the answer. Yesterday we discussed about electric potential. So today we'll see next part of the chapter, capacitance. So what is capacitance? Capacitance is the capacity of a conductor to hold an electric charge for a particular potential difference. Okay, that's the definition. So now how do we find this capacitance? So for an example, suppose you have this conductor, it might be of any shape, and its potential with respect to infinity is suppose V. Okay, so now you call that conductor a capacitor. So suppose there is some charge Q on the conductor which creates the potential V. Okay, then its capacity is equal to what? Q divided by V. Right, this is the formula, Q upon V. So if Q increases, V will also increase. So this capacitance will remain constant. Okay, so because V is directly proportional to Q, we know. Okay, so see, now this is a spherical conductor. So this is a spherical conductor. What would be the capacitance of a spherical conductor? So to find it out, we need to find out what potential difference. So we know potential difference, it's 1 upon 4 pi epsilon naught Q upon R. So suppose there is charge Q, then potential difference will be equal to 1 upon 4 pi epsilon naught Q upon R. Okay, so this is potential on the surface of the sphere, right? And then with respect to infinity, you can say the potential difference is the same. Okay, so you divide C by V, you will get C is equal to, sorry, you divide Q by V, you will get C equals to what? 4 pi epsilon naught R. Okay, so this is the capacitance of a spherical conductor. So we have to remember this formula, C is equal to 4 pi epsilon naught R. After that, so what is the unit of capacitance? So it is Coulomb divided by volt, right? And it is called as Farad. Okay, on the name of great Michael Faraday. So it is known as Farad. And 1 farad is very big unit for a capacitance. So just for an example, so question is find the radius of a metal sphere having capacitance of 1 farad. How big will be a metal sphere whose capacitance is equal to 1 farad? So you just substitute that 4 pi epsilon naught multiplied by R here. So 4 pi epsilon naught, we know it is 9 into 10 raised to 9. Take that 9 into 10 raised to 9 on the other side. Okay, so you get radius equals to what? 9 into 10 raised to 9 meters. Okay, so that is for 1 farad. Okay, so 1 farad is very, very big unit. Generally, the capacitance would be in microfarad. That is 10 raised to minus 6 of a farad. Okay, so now next is the parallel plate capacitor. And this is the most important of all of them. Okay, because there were a lot of questions based upon parallel plate capacitor only, and this is most general type of capacitor that is used in many electric devices. Okay, so let's suppose we have these two plates. The charge on this one is plus Q. Now if this one is charged to plus Q, what will happen to the other plate? The charge minus Q will get induced on it on the other side. Okay, the side which is facing this plate, and you connect an earth supply. So what will happen? The positive charge that will be there on this side, it will go into the earth. So now you have these two plates, one at charge plus Q, the other one at charge minus Q. Okay. So how much is the capacitance of this two plates? So to find it out, we need to find out the electric field. Okay, because finding out electric field will be able to find out the potential. Okay. So now if you consider the three regions, so this is first plate which is charged with positive charge. This is second plate, it is charged with negative charge, and now you want to find out the electric field in this region. Okay, so here and here the electric field will be equal to 0. Why? Because see, the electric field due to both of them will be equal in magnitude, but if you consider this point, so this positive charge, the electric field due to positive charge, it will be in this direction, right? It is radially outwards, you can say. Okay, or it is along the outward normal to this plate. Electric field due to the negative charge, it will be in this direction, right? It will be in this direction. So negative charge will pull any positive charge towards it. Okay, so it is along the inward normal to the plate. Okay, and their magnitude is same because charge on them is same, area of them is same. So sigma upon epsilon naught, sigma upon 2 epsilon naught is the electric field due to one plate. So what happens? The electric field gets cancelled out in this region as well as in this region. Okay, and what happens in this region is, so electric field is along outward normal due to the positive plate. Okay, if you consider this point B, so electric field is in this direction. Due to the negative plate also the electric field is in same direction because it is along the inward normal, right, for the negative plate. But this direction due to the positive plate, the electric field due to positive plate and electric field due to negative plate, they are in same direction. Okay, so they get added. So how much is electric field due to positive one? It is sigma upon 2 epsilon naught. Due to negative one, in magnitude it is sigma upon 2 epsilon naught only. If you add both of them, it will be 2 times of sigma upon 2 epsilon naught, that is sigma upon epsilon naught. Okay, that's the net electric field inside a capacitor, parallel plate capacitor. Is this thing clear? Yes, no? All right. Then we had discussed that the electric field is equal to what? It is negative of the potential gradient, that means potential difference per unit distance, right? So suppose the potential on first plate is V1, potential on second plate is V2. Okay, the electric field will be directed like this. We have just seen it. It will be directed from positive to negative plate. But how much is the magnitude of this potential difference? That we want to find out. Okay, so E is equal to, we can say, minus of V1 minus V2 by D. Okay, so V1 minus V2 will be equal to E times D. What is D? D is the separation between two plates. Okay, so E is potential difference divided by distance, right? So E is constant, that's why we can, instead of taking the derivative, we can just say it is the potential difference divided by distance. Okay, so now you move E on other side, sorry, if you move D on other side, okay, so you get what? Minus of V1 minus V2 is E times D. Okay, or you can take the absolute, uh, okay, absolute value of this, so it will be equal to E times D, right? So how much is this? Put E equals to sigma upon epsilon naught, so you get V equals to epsilon sigma upon epsilon naught times D. Okay, and you know that sigma is equal to what? The charge upon surface area. Put that, you get V is equal to Q upon A epsilon naught times D. Okay, after that you want to find out the capacitance of this thing, the parallel plate capacitor. So you move V on that side and everything else on the other side. So you get C is equal to Q upon V, that is epsilon naught A by D. Okay, from this you get C equals to epsilon naught A by D. So we have to remember this formula very well, that capacitance of a parallel plate capacitor is epsilon naught A by D. Okay, is this thing clear? Yes, no? Okay. Then now suppose you insert some dielectric in between the two plates of a capacitor. So what happens to the electric field? Will be E upon, okay, this original electric field divided by K, right? That means the potential difference will also become what? Because potential difference is E times D, so it will be also E by K times D. So it also falls by K, and the potential is in denominator. Potential difference is in denominator. So what happens to the capacitance? Capacitance C dash will become what? C times K. Okay, it increases K times. If you insert a dielectric instead of air, you insert some other dielectric, then the capacitance of a capacitor will increase by the factor of K. It will be K times the original capacitance. So with dielectric, it is epsilon naught Ka upon D. This thing is clear? Okay. After that, we have a capacitance of concentric hollow spheres. Okay. So see, this thing is, there have been very few questions based upon this, but okay, very few questions. Okay, on this thing and also on cylindrical capacitor. So you just remember the final formula for this thing. Okay, so how do we find this capacitance? To find out capacitance, we'll find out the potential difference between these two, right? This one will be positively charged, this one will be negatively charged. Potential of this one is what? 1 upon 4 pi epsilon naught Q upon R. Potential of this one will be equal to 1 upon 4 pi epsilon naught Q by R, but that R will be different, right? So capacitance of concentric spherical capacitor. Okay, we want to find out. So potential of this one and this one will be 1 upon 4 pi epsilon naught multiplied by Q upon respective radii. Okay, so Q on this one will be positive, Q on this one will be negative, right? So radius of this one is RA, radius of the other one is RB. Okay, so then you find the potential difference. Okay, you find the potential difference between the two. So you get potential difference equals to Q upon 4 pi epsilon naught 1 upon RA minus 1 upon RB, right? So that's the potential difference. And then you move this, okay, this thing on other side, so you get the formula for capacitance. So the formula is C is equal to 4 pi epsilon naught RA RB upon RB minus RA. Or if A and B seems difficult, you can say it is 4 pi epsilon naught R1 R2 upon R2 minus R1. Okay, C is equal to 4 pi epsilon naught R1 R2 upon R2 minus R1. This is the formula. Okay, this thing is clear? Yes, no? All right. So details of how these potentials are calculated and etc. So okay, there is nothing much in detail. See, there will be potential on this sphere due to this sphere as well as this sphere, because we know potential inside a sphere is constant. So potential due to this B inside will be equal at all points, right? So you add potential due to this, okay, plus potential due to this. Also, what you do is you find out potential on this one. So it will be potential due to this sphere as well as potential due to this sphere, right? So potential due to this one. So we had seen the formula. It will be 1 upon 4 pi. So on this sphere, it will be 1 upon 4 pi epsilon naught into Q upon RA. On that sphere, just RA will change to RB, right? Okay. And due to this sphere, the potential here, actually due to this sphere, the potential everywhere is same, right? So it's 1 upon 4 pi epsilon naught minus Q upon RB. And on that sphere, due to that sphere is also same. Okay, 1 upon 4 pi epsilon naught into minus Q upon RB. So when you take potential difference, that term will get cancelled out. That's it. Okay, is this thing clear? Yes, no? Okay. So we need to understand this actually. There can be a question based upon this thing. Okay, but more importantly, just remember this formula. Okay, first of all, remember this formula. Okay, all right. Next one is cylindrical capacitor. There was no question at all based upon cylindrical capacitor. Okay, but it's there in syllabus. So electric field, we know it is minus of dV by dr. So now you have electric field due to a cylinder. Okay, or a charged wire, it is given by this formula, lambda upon 2 pi epsilon naught r. We know this. Okay, so now you want to find out the potential difference. What will you do? You will move this dr on the other side, so you get minus of lambda upon 2 pi epsilon naught r dr, and then you will take integral of that to find out the total potential difference. This is potential difference in small distance dr, right? So then you integrate that and find out the total potential difference between this inner cylinder and outer cylinder. Okay. So you'll find out the total potential difference between inner and outer cylinder. And you call that equal to V. And it comes out to be lambda upon 2 pi epsilon naught log of RB by RA. Okay. Lambda upon 2 pi epsilon naught log of RB by RA. That's the potential difference. Then how much is the charge? So charge would be lambda times L, right? Okay, charge is equal to what? Q is equal to lambda times L, or you can say lambda is equal to Q upon L. So you write that, and then you move these things on left hand side, B on the right hand side, and you find capacitance of cylindrical capacitor, and it comes out to be equal to what? 2 pi epsilon naught L divided by log of RB by RA. Okay, then next is series combination and parallel combination of capacitors. Okay, series combination and parallel combination of capacitors. So what will happen in case of series combination? So suppose you have some capacitors connected to each other in series. Okay, this is how you connect them in series, right? So one plate of this capacitor is connected to one plate of the other one. If both plates are connected, they are in parallel. Okay, and now this combination is given a potential difference of V. So initially suppose they were not charged, and now you are charging these capacitors. So what will happen? So you can think of it like this: some electrons from this negative plate of battery, they come this way. Okay, they travel this way and enter in this plate. So what happens? Some negative charge, let's say minus dq, gets induced here. Same amount of positive charge will get induced on the other plate, right? Same amount of positive charge will get induced on the other plate. Then now what happens? So there will be positive charge. So if you consider this plate, there will be positive charge on this side and negative charge on the other side. So that negative charge will get repelled and it will reach out to this plate. Okay, and because negative charge comes here, what happens? Some positive charge gets induced on this side. Okay, positive positive, and negative charge is repelled by that, so it goes to this plate. Okay, some electrons will move to this plate, and because electrons move to this plate, what happens? They will repel electrons on this plate. Okay, so some positive charge gets induced here and negative charge on this side, so that negative charge flows out toward this positive terminal of battery and it enters the battery, and the flow of charges keeps on continuing. Okay, till the time these capacitors are completely charged, they are charged to their full capacity. Okay, our battery runs out of charges. Is this thing clear? Yes, no? So this is procedure of charging of capacitors. Okay, now in case of series combination, you have the total potential difference. Total potential difference that you apply will be equal to potential difference across these two plates, that's V1. Potential difference across these two plates is V2. Here it is V3. Okay, so potential difference across the plates of capacitors get added to get the total potential difference. Okay, so total potential difference is V. It's equal to V1 plus V2 plus V3. And then you write the total capacitance of series combination is CS. CS is equal to charge divided by potential difference. And we just saw that whatever charge is there on this plate, same amount of charge will be there on all plates. So in series combination, charge on all capacitors would be equal. Okay, what will be equal? Charge on all capacitors will be equal. Okay, so CS is the total capacitance. It's equal to Q upon V, right? So we can find out V, it will be equal to Q upon CS. Similarly, we can write V1 is equal to Q upon C1, V2 is equal to Q upon C2, V3 is equal to Q upon C3, and then we can cancel out Q, okay? And we get 1 upon CS is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, right? So for n capacitors, it will go till Cn, 1 upon Cn. So in case of series combination, what happens? The reciprocal of resultant capacitance, the reciprocal of the total capacitance of a series is equal to the sum of reciprocals of all the capacitors. Okay, capacitances of all capacitors. Okay, so this thing happens for the series combination. Now it's good to remember for two capacitors, it will be equal to what? 1 upon C1 plus 1 upon C2, right? And then we can just find out the CS. It will be equal to what? C1 C2 divided by C1 plus C2. Is this thing clear? All right. The next, in parallel combination, the potential difference is same for all the capacitors because the both the terminals of all capacitors, they are connected to the same battery. That means potential difference across all of them would be equal, right? In series, charge is equal. In parallel, potential difference is equal. And again, now what will happen? So some charge comes out of this plate. So there are two ways at this point. Okay, two paths along which the charge can move. So some charge will enter this plate, some charge will go till here, and again it gets split into two parts, right? So whatever charge comes out of the battery, it gets distributed in three capacitors. So suppose there is charge Q1 on C1, charge Q2 on C2, and charge Q3 on C3. So how much would be the total charge on the combined capacitor? It is just addition of Q1 plus Q2 plus Q3. Okay, the total charge is Q1 plus Q2 plus Q3, right? And then we can say that C is equal to Q upon V. So Q is equal to CV. If you put that for total capacitor, we call it CP. Okay, total capacitance, we call it CP. So total charge is equal to what? Total capacitance multiplied by the potential difference. So again, for total combined capacitor also, it is connected between same two terminals of the battery. Okay, same two terminals of the same battery, and that's why the potential difference would be same. Okay, so Q is equal to Cp times V, and it will be equal to C1 times V plus C2 times V plus C3 times V. V you can cancel out and you get Cp is equal to C1 plus C2 plus C3. So in case of parallel combination, the capacitors get added to get the total capacitance. This thing is clear. Let's come to dielectrics and polarization. What do you mean by a dielectric? Dielectric means insulators. Okay, dielectric means what? Insulators, and they can be used to store electrical energy. Okay, now there are two types of dielectrics. So one is polar dielectric, the another one is non-polar dielectric. Polar means what? So if you consider molecule of this kind of a material, okay, then it will have permanent dipole moment. For an example, you have HCl. So HCl has H positive ion, Cl negative ion. So there is a permanent dipole moment from Cl negative to H positive, right? H2O. Okay, here also you have H plus ion, right, and O minus 2, right? Sorry, O2 minus ion. So what happens here also, there will be a resultant permanent dipole moment in this direction. Okay, there will be one dipole in this direction, one in this direction, resultant of them will be like this. So these kind of substances, they are called as polar dielectrics. They have, each molecule has a dipole moment. Okay, each molecule acts like a dipole. Yes. Then there are molecules like this, for example H2. So this one doesn't have a dipole. Then CO2, it depends on the alignment. Okay, so CO2 is aligned like this, so this one also doesn't have a dipole. Okay, so now we don't have to remember here the alignment of all the molecules, etc. So just the difference between polar and non-polar. Okay, so the definition goes like this: the center of mass of positive charge and the center of mass of negative charge is same, then it is non-polar. Okay, see here, if you consider nucleus of this one, nucleus of this one, then what is center of mass of the positive charges? Okay, it is proton, this proton and this proton, so it's here. What is center of mass of these negative charges, the electrons? It's also the same, right? So for non-polar molecule, center of mass of the positive charges and center of mass of negative charges is same, then the molecule is known as non-polar molecule. Okay, and in case of polar molecule, it is different. Okay, all right, so that's another point. And then HCl, water, alcohol, NH3, these are some examples of polar dielectrics. Some examples of non-polar dielectrics are H2, O2, CO2, benzene, methane, etc., etc. Okay, so as far as physics goes, you don't need to remember these examples also. One or two you can remember. Okay, you can just remember wherever you have the ionic bond, they are what? Polar dielectrics. Wherever you will have covalent bond, now orientation will matter. Okay, so actually this one is also, this one is not covalent, this is ionic. Yeah, wherever you have covalent bond, I can say that it will be non-polar, right? For an example, you have Cl2 also, so it will be non-polar. Okay, all right, so then next, suppose this dielectric, polar or non-polar, if you keep it in external electric field, what happens? So for polar dielectric, these individual dipole moments of all molecules, they will be aligned in different directions, right? Because due to their thermal energies, you can say they will be keep on moving also. Okay, I mean they will be keep on vibrating. Okay, and they will be directed, the individual molecules, the dipole moments of individual molecules will be directed in different directions. So when there is no electric field, but when you apply the electric field, we know that what happens to the dipole in electric field exerts a torque on it and it tries to align it in the same direction as that of electric field. Okay, so since earlier these dipoles were directed in different direction, the net dipole moment was zero. Now they get aligned in the same direction as that of the electric field. So now there will be some permanent dipole moment because dipole moments of all of them will get added, right? So this phenomenon is known as polarization. Okay, this phenomenon is known as what? Polarization. Okay, so some dipole moment gets induced due to the external electric field. This is known as polarization. Is it clear? All right. Then for case of non-polar dielectric, here also polarization will happen. So you might say now there are no dipole moments. Okay, the center of mass of positive and negative charges, they are the same. So see, now suppose you have a nucleus like this and electrons are like this. Okay, surrounding the nucleus. What happens if you apply some electric field? The electrons, they are pulled by the electric field and the nucleus will get pushed, right? So nucleus won't move much, but electrons will move, right? So if there is electric field like this, electrons will move in the opposite direction of electric field. So the center of mass of positive and negative charge, which was same earlier, now it becomes different because nucleus will stay there. Okay, nucleus will stay there and electrons will move like this. Electrons which were here, they will move. Okay, so now there will be some separation between the positive and negative charges. Okay, so earlier the center of masses were same. Now electrons are pulled. Okay, so you can see the dipole moments are produced. Okay, you can see means in the diagram. Okay, so dipole moments are produced, so induced in the dielectric, and they get aligned in the direction of external field. Okay, so again, what happens? The polarization happens in case of non-polar dielectric also. Okay, after that, how do we define this polarization, strength of polarization? So if suppose there are n number of molecules, then the individual dipole moment of all of them, suppose p bar, small p bar, so total dipole moment will be n times p. Okay, and this total dipole moment will be n times p, we divide it by volume. So the polarization is defined as what? Np bar upon volume. Okay, then now for an isotropic material, so isotropic means the polarization happens equally in all directions. So for that kind of material, polarization is just directly proportional to external electric field. Okay, so see, this is now suppose you apply electric field in some direction. So this is like a common sense if we don't think much. Okay, and in 12th standard, thinking too much is not there in our syllabus. Okay, so for a material, polarization happens because of electric field, right? So more is the electric field, then more will be polarization. Yes, no? Okay, so p bar is directly proportional to what? The external electric field, and p bar can be written as it's equal to some constant times external electric field, and that constant is known as the susceptibility of a dielectric material. Okay, susceptibility of the material, electric susceptibility of the material. So p bar is equal to chi times E. Okay, and the chi is known as what? The susceptibility of material, right? So there were no questions based upon this thing directly. Okay, but there can be, right? So is this thing clear? So what I mean when I said that we are not allowed to think too much in our syllabus. So actually, in higher levels, you will see that the polarization depends on electric field. It also depends on direction. It also depends on second power, third power of electric field, etc., etc. Okay. So here we consider linear relation. The actually for most of the cases the relation will be linear, but for few cases it will be non-linear. Non-linear means there will be second power of electric field, third power of electric field, etc., etc. Okay. All right. So that thing doesn't matter for us. Here I have just shown the dielectric. Then effect of dielectric on the capacitance. So now suppose you insert a dielectric slab, what happens to the capacitance? Okay, so this thing actually we just have to remember the direct formula for this case. So suppose you insert dielectric, what happens to the electric field? Electric field just becomes what? The original electric field, sigma upon epsilon naught divided by k. Okay, so E dash is just equal to what? Epsilon naught divided by k. So this derivation etc. we don't need to remember. So suppose you insert a dielectric slab having thickness equal to T. The total distance between two plates is equal to D. the thickness of this slab is equal to T. Area is equal to area of these plates. Okay. So then what happens to the capacitance? Once again, there is a long derivation. We don't need it. So capacitance becomes epsilon naught A d minus T plus T by K. Okay. If there was air earlier, now you insert a dielectric slab. Capacitance becomes epsilon naught A d minus d minus T plus T by K. Okay. So you can remember this relation. Even if you don't remember, it won't matter much. There is another way in which we can solve it. Okay. So yeah, after that, so this specific case, actually we have discussed this earlier, that what happens to the capacitance when you insert dielectric in between plates of the capacitor. So capacitance becomes what? K times the capacitance, original capacitance, right? Because electric field falls by E by K. Okay. So then now suppose you have these, suppose you have this capacitor, and in between these two plates you insert dielectric like this. Okay, now what will happen? So you can think of these dielectric slabs like various capacitors. Okay, so from here to here there are two plates. This is like you have two plates. Okay, and here the dielectric constant is K1. Here you have dielectric constant K2. Here you have dielectric constant K3, so on and so forth. So now n slabs are inserted in between two plates of capacitor. It's like you have n capacitors having various dielectrics, right? So what will be the total capacitance of this thing? It will be just series combination of all these capacitors. Is this thing clear? Yes, no? All right. And then now if you insert it like this, okay, K1, K2, K3, these dielectrics like this. So again, you are inserting some dielectric in between two plates, but now they are not slabs. Okay, up to this much area, suppose you insert one dielectric. Okay, end to end between two plates. Okay, for this much area, you insert this another dielectric. It's K2. Here you insert another one. Here you insert another one. This is like a parallel combination of various capacitors. So this is one capacitor, this is another capacitor. You can say plates, both plates of these capacitors, they are connected to each other, right? So this is like a parallel combination. This one was like a series combination. This one is like a parallel combination. So what will be the net capacitance? So find out capacitance of this one, this one, this one, this one, and add it up. You will get total capacitance, because capacitance gets added in case of parallel combination. Okay. So just remember that areas will be different in this case. Okay. So for first one, it will be epsilon naught A1, sorry, K1 times, K1 is dielectric constant. So K1 times epsilon naught A1 divided by D. Okay, D is same for all. For second one, it will be K2 times epsilon naught A2 upon D. And for nth one, it will be Kn times epsilon naught An upon D. Right? So remember, this is the parallel combination. This is the series combination. Okay. So there were questions a few times based upon this thing. This thing is clear? Yes, no? All right. After that, next point is charging of a capacitor. Okay. And this is also an important point. So suppose you have this capacitor, you apply some potential difference here. So now some charge, suppose this capacitor is charged up to some charge, let's say Q. Okay. So now it is not charged fully. So what happens if there is already some charge minus Q and these electrons are coming from this side? So these electrons will get repelled by the already present negative charge there, right? Yes, no? So this battery will have to do some work in order to deposit more negative charge on this negative plate of capacitor. Okay, so that work gets stored as the potential energy of the capacitor, right? So how much is the work done? So work done is potential difference multiplied by the charge that you are storing. Okay, and what is potential difference? So we know C is equal to Q upon V. So potential difference will be equal to what? Q upon C. So then this is small work done to store charge dq. Okay, so what will be total work done to store the charge q? So it is just integral of this thing from 0 to q. Okay, so total work done is just integral of q dq by c from 0 to q, and integrating you will get what? So this integral is simple, it is just q raised to, this is 1, q raised to 2 divided by 2. Okay, so you get work done equals to q square upon 2c. That means the potential energy of capacitor is q square divided by 2c. This thing is clear. Then you have different formulae for potential energy of a capacitor. So one is q square upon 2c. Then you can substitute q is equal to cv here. So it will be c square v square divided by c. Okay, and then one of the c will get cancelled. So you get this formula, u is equal to half of cv square, right? Then you can write this is half of cv square. Okay, so again what you can do, you can write v is equal to, okay, you can change this, either you write c or v in terms of q. So you get this another formula, it is half of q times v, right? So you have to remember this formula as well as this formula. This one, if you want, you can remember. If you don't want, don't remember. Okay, but we can always find out, given the potential difference and the charge, okay, what will be the energy stored, right? Yes, no. Even if you don't remember this, you can find out C is equal to Q by V. If you are given with Q and V, you can just find out C equals to Q by V. Then you know V and you found out C, so you can use this formula. Okay, but this one and this one is important because they will be directly used in most of the questions. Okay, so we have to remember energy stored in capacitor. Then we also have to remember energy stored per unit volume of the capacitor. Okay, so this is the energy stored, it is half of q square by c. And what is volume of the capacitor? It is area multiplied by the distance between plates, right? The capacitor is like this is first plate, this is second plate. So area is a and distance between two plates is d. How much is volume here? It is this d multiplied by this area, it is like a cube. Okay, so energy per unit volume is denoted by the small u, it is equal to capital U divided by volume, and volume is A times D. So you get this formula. Okay, it is half of Q square by C into A times D. Okay, then now what we can do is we can write the C as epsilon naught A upon D. Okay, this D and D will get cancelled, and you will get energy stored per unit volume is q square upon epsilon naught a square, half of q square upon epsilon naught a square. So you know sigma is equal to q upon a. So you can write the energy stored as half of sigma square, because it is q square by a square, it becomes sigma square. So it is half of sigma square upon epsilon naught. That is the energy stored. Okay. Then you can write it in other form, right? Because electric field is equal to sigma upon epsilon naught. So you can write sigma is equal to epsilon naught times E. And then you get this formula, the energy stored per unit volume is half of epsilon naught E square. Okay, this is clear. All right. So these are the very few things that we need to remember for a capacitor. Okay. And now we will solve some problems. So will solve from this one. Okay, parallel plate capacitor is constructed using three different dielectric materials as shown in the figure. Like this, the parallel plates across which the potential difference is applied is of area a meter square and separated by distance d meters. The capacitance across A and B is. So tell me, what will you do? K1, K2, K3. Which ones are in series? Which ones are in parallel? So see, it's not correct, because if I draw it like this, okay. So here you have this K2 and K3. This is series or parallel? The series combination, right? Okay, they are not in parallel. So this plate, and if you have dielectric inserted between two plates, okay, so in half of it, or whatever thickness, you have dielectric of constant K2, suppose, or whatever, and in other half you have different dielectric constant, then those two are in series, they are not in parallel. Okay, so this one and this one. So now if you find out the total capacitance of this thing, so you will get some capacitance, it is in parallel with this thing. Okay, here you have capacitance K1, right? Because both plates of this combined capacitor, both plates are connected to this one, so it is parallel now. Okay, so this is simple, right? So just find out the equivalent capacitance of this thing. So let's find out CS. Okay, so what is CS? We can say 1 upon CS is equal to 1 upon, uh, here it's C2, right? C2, because it is K2, and plus 1 upon C3. That is equal to 1 upon, how much is C2? Epsilon naught K2 multiplied by A2 upon the distance. Okay, K2 upon A2 by D2, you can say, plus 1 upon epsilon naught K3 A3 upon D3. So now you can see how much is the area and how much is the distance between the plates. Okay, so area A2 is equal to A by 2, and D2 is also equal to D by 2. So that 2 will get cancelled. So this is A by D, right? Yes, no? Okay, all right. Then I can say that this D will go in numerator, D will go in numerator. So you have 1 upon CS, therefore 1 upon CS is equal to, D will be in numerator, epsilon naught K2A, plus D will be in numerator, epsilon naught K3A, right? That was A by 2, D by 2. So 2 got cancelled, and D I am taking in numerator. Okay, so you can take something common, D upon epsilon naught A, you can take common. This is 1 upon K2 plus 1 upon K3. This is 1 by CS, and then you can write down what is CS. So CS will be equal to what? This thing you can say it's K2 plus K3 upon K2 K3. Take reciprocal, it will be epsilon naught A times K2 K3 divided by K2 plus K3 and D. So you got CS. Okay, what about this thing? So this one is, what is that? T1. T1 is equal to, so the separation is D. Okay, separation is equal to D, but area is equal to what? A by 2. So how much is the capacitance? it is equal to epsilon naught K1 A by 2 and separation is D, right? I wrote A by, so epsilon naught K upon D, but A is equal to A by 2, right? Got it? Yes, no? So just add it up, you get total capacitance. So the total capacitance of this parallel combination now will be equal to Cs, okay, plus C1. That is equal to epsilon naught A K2 K3 upon K2 K3 divided by D times K2 plus K3 plus epsilon naught A K1A, so times K1 upon 2D, okay. Okay, so you can take something common, epsilon naught A by D, you can take common, epsilon naught A by D, you took common, then it is K2 K3 upon K2 plus K3 plus K1 upon 2. So this is the answer. Okay, so let's check which one. K1 upon 2 is there in this option only, and K2 plus K3 upon K2 K3. No, it's there in this one also, right? K2 K3 upon K2 plus K3. This is the answer. Got it? Yes, no? Okay, will you be able to solve this kind of a question? Okay, good. Let's see. Here you have a parallel plate capacitor with air as a dielectric, has capacitance C, a slab of dielectric constant K, and having same thickness is same, as that of separation between plates is introduced so as to fill 1/4 of the capacitor as shown in the figure, the new capacitance will be. This is simpler than the last one, right? So tell me, how much will be the new capacitance? These two are in series or parallel? These two are in parallel. Mhm. Okay. Epsilon naught K A1 by D. D is same for both of them, plus epsilon naught K A2 by D. But there is no K, there is air. Okay. So epsilon naught A2 by D. Right. So then how much is the area? How, so this is filled in, okay. So a slab of dielectric constant K and having same thickness as that of separation between plates is introduced as to fill 1/4 of the capacitor. So this is 1/4 they are saying. So T is equal to 1/4. Okay, we called it D. So D is equal to 1/4, right? So this area will be equal to 1/4 of total area. Okay, so you can say that this thing area A1 will be equal to what? 1/4 A by 4. So what will be A2 then? T A by 4, 3/4, right? So you can substitute that. So you will get epsilon naught multiplied by K A by 4 plus 3 times epsilon naught A divided by D. Okay, and epsilon naught A by D we can take common. Okay, and there will be K by 4 plus 3, right? This is the original capacitance. Okay, C, sorry, C, and what will be this thing? It is K plus 3 times 4 is 12. Okay, K plus 12. It's not matching. Oh, this will be 3 by 4, no? Okay, so it is 3 by 4, right? You can take that 4 also outside, and then it will be K plus 3 only. So which option? So this is 3 dash. You got it? Yes, no? This is option A. Okay, I didn't take this 4. Okay, it will be 3 by 4, right? Here I wrote A by 4, here I wrote only 3. So it will be 3A by 4, right? A2 is 3A by 4. Okay, so this is clear. This is simpler compared to last one. Okay, good. Then next, the energy stored in a capacitor of capacity C and potential V is given by. Okay, this is just, tell me, half of CV square, option D. Next one, a capacitor is charged with a battery and energy stored is U. After disconnecting the battery, another capacitor of same capacity is connected in parallel to the first capacitor. Then the energy stored in the capacitor is. So tell me. Okay. So when you charge first one with a battery, energy stored will be equal to half of what? Q square by C. Right? Now you connect another capacitor. So this one is charged. Okay, there is charge plus Q and minus Q. So this is uncharged. When you connect them together, the second one will get charged. So charge on second one will increase, charge on first one will decrease. Okay. What about the total charge? Total charge remains constant. Okay. So now whatever happens, it's energy, final energy. This is initial, you can say, initial potential energy, and final potential energy. Suppose U dash, it will be equal to half of final charge square upon final capacitance. Charge remains constant, right? So it will be Q square divided by what happens to the capacitance now. So capacitance is Cp, it is equal to P plus C, 2C, right? So it is equal to 2C. So what has happened to the energy? It is half of Q square by 2C. It is half of Q square by 2C. Okay. That means it is half of U, right? So its answer is option A. Okay. So this kind of a question has been repeated sometimes. Okay. So we need to understand this procedure, what's happening actually. All right, let's see next one. Energy per unit volume for a capacitor having area A and separation D kept at a potential difference V is given by. Tell me this one. They want energy per unit volume. What's the formula? The regular formula that you know. Yeah. So U is equal to energy per unit volume. It's half of epsilon naught E square. Then very good. So E can be written as V upon D. So it will become half of epsilon naught V square by D square. Option A, right? Okay. Let's see next one. Two condensers, one of capacity C and other of C by 2 are connected to V volt battery. Okay, this one as shown in the figure. The work done in charging fully both condensers is, condenser means capacitor. Okay, earlier they used to write condenser. Okay, so tell me, what will you do to find out work done? It's just half of CV square, right? You have C, you have V, but what will be the capacitance? It will be Cp, because this is parallel combination of the two capacitors, right? They are connected in parallel, so it will be Cp. It is C plus C by 2, which is 3C by 2, right? And therefore, the energy or the work done will be half of Cp into V square. V is same for both of them. So it is half of what? 3C by 2 into V square. Or you can say 3 by 4 CV square. This is the answer, right? Option B. Okay. Next one, a series combination of N1 capacitors, each of value C1 is charged by a source of potential difference 4V. In another parallel combination of N2 capacitors, each of value C2 is charged by a source of potential difference V. It has same total energy stored in it the first combination has. Okay. The value of C2 in terms of C1 is then. Okay. So now if you connect N capacitors in parallel having capacitance C, what will be their capacitance? If you connect 2, it will be C plus C, right? 2C. If you connect 3, it will be 3C. If you connect N in parallel, it will be NC. And for series, it will be what? C upon N. Okay. For series, it will be C upon N. So series combination of N1 capacitors. So CS is equal to what? It is equal to C1 divided by N1. Okay. It's charged by potential difference of 4V. So V1 is equal to 4V. And now you have N2 capacitors which are connected in parallel. So Cp is equal to N2 times C2. Okay. Their capacitance is C2. And they are charged by potential difference V. V2 is equal to V. And they have same energy. Okay. So U1 is equal to U2, right? So half of CS into potential difference is V1. Okay, that is 4V, or I will just say V1 square is half of Cp times V2 square. Okay, now let's substitute the capacitance and potential difference. So CS is equal to what? C1 upon N1 multiplied by V1 is 4V. 4V square is equal to Cp is N2C2 times V square. Okay, V square will get cancelled and 4 square is 16. So you have C1 upon N1 into 16 is equal to N2C2. Okay, the value of C2 in terms of C1 is, take N2 on other side. You get C2 equals to C1 divided by 16 C1 upon N2. Right, so this is simple. Okay, there was nothing in that question, right? A parallel plate capacitor has uniform electric field E in the space between plates. If the distance between plates is d and area of each plate is a, the energy stored in capacitor is. Okay, tell me. You know energy per unit volume. U is equal to what? Half of. Okay, so whenever they ask questions like this, start with this formula. Okay, this is energy per unit volume. Yes. Exactly. So this is U upon V, but V is volume. Okay, is half of epsilon naught E square, and volume is A times D. You can move that on other side. So it is half of epsilon naught E square times volume, which is A times D. Good. So it is option C, right? Okay. Next one, a parallel plate air capacitor of capacitance C is connected to a cell of EMF V and disconnected from it. Our dielectric slab of dielectric constant K, which can just fill the air gap of capacitor, is now inserted in it. Which of the following is incorrect? The change in energy stored is half of CV square 1 by K minus 1. We have to check this. The charge on capacitor is not conserved. Okay. The potential difference between the plates decreases K times and the energy stored in capacitor decreases K times. Can you tell me which one is correct? Right. Exactly. Option B is incorrect. So this is the answer. Okay. Potential difference decreases K times. We have discussed. Energy stored decreases K times. This can be found out. Okay. And change in energy stored is half of CV square. So if we find this thing will be proved because they say that energy stored decreases K times. Okay. So if it decreases K times, originally if it was half of CV square, now if it becomes, okay, this is u dash, if it is equal to half of CV square divided by K, that means the change in energy u dash minus u will be equal to what? Then delta u is final minus initial u dash minus u will be take half CV square common 1 by K minus 1. This is proved, right? Okay. So is the change in energy uh, if the change in energy decreases K times, that you have to find out. Sorry, if the energy decreases K times. So see, u dash will be equal to what? It is half of C dash times V dash square. So C dash becomes K times C and V dash becomes what? V by K. Okay. So then you have K square in denominator, one of that gets cancelled out. So it is actually 1 by K times half of CV square. That is true. Okay. It becomes U by K. So this thing is correct, right? So if this thing is correct, this one is also correct. Is this thing clear? Okay, good. So you should be able to find it out, right? But it's good that you answered. The charge on the capacitor is not conserved. If you know this, don't need to think about these things in exam. Okay, let's see next one. A capacitor is charged by a battery. The battery is removed and another identical capacitor is connected in parallel. The total electrostatic energy of the resulting system. We have solved this. This was the, okay. Yeah, tell me. Capacitor is charged. Then you remove the battery. Another capacitor is connected. What happens? Decreases by a factor of 2, right? We have solved this question. It is this one. Okay, so this is repeated. Let's see next one. Two identical capacitors C1 and C2 of equal capacitance are connected as shown in the circuit. Terminals A and B of the key are connected to charge capacitance C1 using battery of EMF V volt. Okay. Now disconnecting A and B, you can disconnect this key and the terminals B and C are connected. Now these two are connected. So once again you are doing the same thing. Okay. You are charging this capacitor by a battery and you are disconnecting battery, connecting another capacitor. Okay. Due to this, what will be percentage loss of energy? So again, these are identical capacitors. That means this is C1 is equal to C, C2 is also equal to C. Tell me how much is percentage loss? 50%. Okay, energy becomes half, right? So it is option C. This is repeated, okay, many times. Let us see next one. A parallel plate capacitor of area A, plate separation D, and capacitance C is filled with four dielectric materials having dielectric constant K1, K2, K3, K4 as shown. Okay, in the figure, if single dielectric material is to be used to have same capacitance C in this capacitor, then its dielectric constant K is given by. Okay, so once again it is similar question. So tell me, what can we do? These three are they in series? This is the plate. This is another plate. They are in parallel, no? Okay. So, okay, they are in parallel. Their capacitance will get added. So let's find out Cp first for this one. Okay, so Cp will be equal to what? C1 plus C2 plus C3. That is epsilon naught, yeah, Ka upon D. That's the formula. K1 A1 upon D1 plus K2 A2 upon D2 plus K3 A3 upon D3. Okay. So epsilon naught K2 A2 upon D2 plus epsilon naught K3 A3 upon D3. But what is A1 A2 A3? A by 3 A by 3 A by 3. D1 D2 D3 is D by 2 D by 2 D by 2. It's same, right? So we can write this as A by 3 and this one as D by 2. So that 2 goes to numerator. We can say it is 2/3 of A by D. Okay. So let's write 2/3. So instead of writing everywhere, I will just say this 2/3 of this. Okay. And then also we can take some things common. Epsilon naught A by D we can take common. So we can say, okay, it is equal to 2/3 of epsilon naught A by D K1 plus K2 plus K3, right? So this is for parallel. Then this one and this one are in series. Okay. So let's add page here. So how much is that capacitance? It's K4, C4. Okay. So 1 upon Cs is equal to 1 upon Cp plus 1 upon C4. And how much is that epsilon naught? So this one we can write, this thing is in numerator. So whatever is in numerator, it will go in denominator. Denominator goes to the numerator. So it is 3D upon 2 times epsilon naught A, sorry, 2 times epsilon naught A, K1 plus K2 plus K3. I have just written reciprocal of that parallel combination. And C4 is epsilon naught K4 times A4 upon D4. So what is A4 and D4? A4 is total area A, D4 is D by 2, right? A4 is A, D4 is D by 2. So that D by 2 will come here. Then you want the dielectric constant of this thing. Okay. So if this is one capacitor, then how much would be the dielectric constant? That is the question. Okay. So you say that this is one capacitance. So suppose capacitor can be written as what? D upon, I mean, it's reciprocal. D upon epsilon naught, let's say Ks times A. Epsilon naught Ka by D, its reciprocal will be D upon epsilon naught Ka. Okay, so this can be written as D upon epsilon naught A. Will take common from both of them, and it is 3 by 2 times K1 plus K2 plus K3 plus 1 by 2 K4. Okay, so this thing will get cancelled, and this is the answer. 1 by Ks or 1 by K, you can say, is equal to this thing. Option C. Okay. So this is also simple, slightly lengthy, but simple question, right? Okay. Let's see next. Two thin dielectric slabs of dielectric constants K1 and K2 are inserted between the plates of a parallel plate capacitor as shown in the figure. The variation of electric field E between the plates with distance d as measured from plate P is correctly shown by, tell me, these are plates. Wherever you have plates, electric field will increase or decrease? It will decrease because it's E by K. And if K is more, it will decrease more. If K is less, it will decrease less. Okay. Where is it decreasing? So in first one, it is see from here to here, it's this much. Then wherever you are inserting plate, here it's increasing. So this cannot be correct. Okay. In this one, it is decreasing, and K2 is more, so it is decreasing more. So this one is correct, right? Option C. Okay, so this is simple. Let's see next. Two parallel metal plates having charges Q plus Q and minus Q face each other at certain distance between them. Plates are now dipped in kerosene oil tank. The electric field between the plates will. Yeah, this is very straightforward. Okay, decrease, correct. Next one, the capacitance of parallel plate capacitor with air has medium 6 microfarad. With the introduction of dielectric medium, the capacitance becomes 30 microfarad. The permittivity of the medium is, okay, tell me. That is fine, but earlier you had air. Now you are inserting a dielectric. What is that relation? C AC, K times C, right? So you can find out dielectric constant from here. Okay, so this is 30 microfarad is equal to K times 6. So K is equal to 5. But do you want dielectric constant? No, you want permittivity. So what is permittivity? Epsilon. It is epsilon not K, right? So there is nothing in the question. Epsilon naught is 8.85 multiplied by 10 raised to minus 12 and into 5. So this will be almost 9 times 5, you can say 45. Okay, 45 times 10 raised to minus 12 or 4.5 into 10 raised to minus 11. This is the answer. Not that? Okay. Or you can say 0.4. Okay. Don't know why they do this, but it's okay. Generally, it has to be written like this. Okay. This is the scientific form. All right. So just to create confusion, they wrote it like this, but that's fine. This is clear. Okay. Yeah. Question in itself was not difficult, so they created some difficulty or confusion here. Anyways, next one. When a capacitor is connected to a battery, option A current flows in the circuit for some time, then it decreases to 0. Option B, no current flows in the circuit at all. Option C, an alternating current flows in the circuit. Okay. Option D, none of the above. Yeah, it's option A. Right. Current flows for some time. When capacitor gets charged, after that, no current will flow. So if you think of capacitor as a single topic, you can see how many number of questions have been asked. Okay, so this is an important topic, capacitor. A spherical drop of capacitance, and the questions we discussed, most of them are NEET questions. Okay, AIPMT NEET questions, right? So I have taken some questions from other exams also, just to because some topics are important. Okay, so there can be slight variation of questions. That's why I take some questions from other exams also. Okay, but most of them are from NEET. Okay, or AIPMT. All right. So a spherical drop of capacitance 1 microfarad is broken into 8 drops of equal radius. Then capacitance of each small drop is. So first of all, you tell me how much is capacitance of, or what is the formula for capacitance of spherical capacitor? Is equal to, this is very simple, 4 pi epsilon naught r. We started with this, right? So one spherical drop of capacitance is broken into 8 drops of equal radius. So what can you say? So volume of one big drop, yeah, volume of one big drop, or big sphere, I can say, big sphere equals to 8 times volume of small sphere. So this is 4 by 3 pi r cube equals to 4 by 3 pi, sorry, 8 times small r cube times 8. Okay. So volume is directly proportional to r cube. You can directly start from r cube. Capital R cube is equal to 8 times small r cube. Okay, or whatever number is given, you can start with that if there is a question like this. So this type of a question is asked in capacitor. Same type of question is asked in surface tension, right? Okay. So here, yes, capital R is 2 times of small r. Good. So now C dash will be equal to 4 pi epsilon naught multiplied by small r, which is capital R divided by 2. Okay, so C dash is equal to, therefore C by 2. What is the answer? Half microfarad. First one was 1, no? So now it becomes half. Okay, so this is also a simple question. Let's see next one. The capacitance of two concentric spherical shells of radii R1 and R2 is. Tell me. Okay, good. Option C. Next one. In a parallel plate capacitor, the capacity increases if area is decreased. Will it increase? So our formula is epsilon naught Ka, or divided by D. Okay. So if area is decreased, capacitance will also decrease. Okay. Distance between plate increases. Then if you increase the distance, capacitance will decrease. Okay. Area is increased. So this is the answer, right? Capacitance will increase if area increases, because it is directly proportional to area. Okay. Let's see next one. What is effective capacitance between point X and Y? This is old question, but this is nice question. Okay. See, this thing, if there is a combination like this is Wheatstone's bridge, which we'll learn in next chapter actually. Okay. So we learn it for resistors. You have a resistor like this. This is one resistor. This is another resistor. This is one. And okay. So there are these resistors R1, R2, R3, R4. So if R1 by R3 is equal to R2 by R4, or R2 can be here, R3 can be here. If R1 by R2 is equal to R3 by R4, then this branch is ineffective. Okay, this branch is ineffective, right? So these two will be in parallel. These two will be in parallel. These two will be in parallel. Got it? Okay, that is for Wheatstone's bridge. Okay, then see how this thing is Wheatstone's bridge. So here you have A, C, B. So it's like this is okay, this is like this is B, A, B, C, D. Okay, so you see between B and C, one resistor is here. Here you have one capacitor. Okay, between B and A, you have this one capacitor connected. So it's like this resistor. It is connected here. Okay, between C and A, this one is connected. Okay, so if I redraw it, if I draw B here, C here, so in between B and C, you have one capacitor. In between, yeah, that is 20 microfarad. Okay, between B and A, you have this one capacitor. Okay, so if I say A is here, between B and A, what's there? One capacitor is there. Okay, it is of 6 microfarad. In between A and C, also one capacitor is connected, that is 6 microfarad. Between B and C, yeah, B and C, we already connected one. B and D, so it's like this, 6 microfarad. Okay, and between D and C also again, there is one capacitor of 6. Okay, so it is this thing only, Wheatstone's network, nothing else, right? Is it balanced? Balance means, is this capacitor upon this capacitor equal to this upon this? Yes, because all of them are 6 6. Okay, so this is ineffective. We don't need to think about this capacitor. Okay, so remove that and you will have the capacitance between A and D, or which is X and Y. Okay, capacitance will be 6 and 6. Right, the 6 6 6 6. So these two are in parallel, these two are in parallel. Okay, so this thing is how much? 12, right? Sorry, this is in series, this is in series. So this thing is how much? 3. This thing is how much? 3. So 3 and 3 in parallel. So it is 3 plus 3. How much? 6. Okay. So here you remember one more thing. If you have equal capacitors connected in bridge combination and a bridge is balanced, of course it will be balanced. Then effective capacitance would be equal to what? Capacitance of one capacitor. Okay, if you have equal resistors connected in the bridge combination, then also the equivalent resistance will be equal to what? The resistance of one resistor. Okay, so what's the answer? 6. Okay, let's see next one. Capacitor of capacitance C1 is charged up to V volts, then connected in parallel to uncharged capacitor of capacity C2. The final potential difference across each will be. Okay, so how will you find it out? What will be the final potential? So first one is charged up to V, right? First one is charged up to V. Okay, you have this first capacitor C1. So there will be some charge plus Q and minus Q. Okay, and it is charged up to potential difference V. Potential difference is V. So how much is this charge then? Q is equal to C1 times V, right? Now what you do? Now you are connecting some other capacitor. This is C1, this is C2. Okay, so now charge will flow from this side to this side. Okay, so now suppose charge on this one is Q1, charge on this one is Q2. But what can you say about the charge? We have discussed this. Total charge remains conserved. That is equal to Q, right? You can say Q1 plus Q2 is equal to Q. Okay. Yes, no. Okay, so Q1 plus Q2 is equal to Q. All right. So now they are connected in parallel. So potential difference across them will be equal, right? So how can you write this charge Q1 and Q2? Q1 you can say it is equal to C1 times whatever is potential, and Q2 is C2 times whatever is potential. So that is equal to Q. So Q is equal to C1 times V. And you want to find out this potential difference. Okay. So take this thing common. So you will have C1 plus C2. Move it on other side. This potential difference will be equal to C1 divided by C1 plus C2 times V. Right? Got this? Yes, no? Okay. So this is also simple question. Okay. So this is also kind of same thing. The two, you have one charged capacitor, you remove the battery, connect other uncharged capacitor. So key thing is this thing, charge remains constant. Okay, if you remember this, then you can find out. This thing is clear, yes, no? Okay, good. Let's see next one. Three capacitors, each of capacity 4 microfarad, are to be connected in such a way that the effective capacitance is 6 microfarad. This can be done by, okay, you have three capacitors, 4 microfarad, and you want effective capacitance equal to 6. Connecting all of them in series, connecting them in parallel, connecting two in series, one in parallel, connecting two in parallel, one in series. Tell me. Okay, all of them in series, 1, 2, 3. Okay, this is 4, 4, 4. What will be CS? It is 4 by 3. Okay, do you want 4 by 3? You got this? Yes, no? Okay, so CS is 4 by 3. No, you don't want 4 by 3, you want 6 microfarad. Okay, if you connect them in parallel, 1, 2, 3, parallel. Okay, so what will be equivalent? CP equals to 3 times whatever is capacitance, 4. Okay, so that is 12. We don't want 12 also. Okay, so we can try doing this. 2 parallel, 1 series. Okay, or what else can we do? 2 series and 1 in parallel with this series. Okay, so this question has to be solved like this only, trial and error. Okay, there is, I mean, no shortcut to this. Okay, so see, this is 4, this is 4. 2 in parallel. What will be the resultant of this thing? 8. Right? CP is equal to 8. Yes, no? This is 8 and you have 4 in series. So CP is equal to 8. So you have 1 upon CS is equal to 1 upon 8 plus 1 upon 4. This is in series. Or you can just say CS is equal to 8 times 4 upon 8 plus 4. 8 plus 4 is 12. 8 plus 4. So this is 32 divided by how much? 12, right? Yeah, 32 upon 12. This is also not 6, right? This is 16 by 6 or 8 divided by 8 by 3. This is 8 by 3. Okay. All right. So this is the answer then, 2 in series, 1 in parallel. Okay. So 4 and 4. What is the equivalent of this one? 2. Okay. Then 2 and 4 in parallel. So this thing is 2. 2 and 4 in parallel. So equivalent is 6 microfarad. This is the answer. 2 in series, connecting 2 in series and 1 in parallel. This thing is clear. So there is no shortcut in this. It has to be solved like this. Okay. Connecting all of them in series, this will not work. This can be done very fast. Connecting them in parallel, this will also not work. So yeah, it won't take much time. This is third option. Okay. It will not take much time, right? If options are like this. If options are different, we have to try those combinations. Okay. Let's see next one. A network of 4 capacitors of capacity equal to C1 is C, C2 is equal to 2C, C3 is equal to 3C, and C4 is equal to 4C are connected to a battery as shown in the figure. Ratio of charges on C2 and C4. Where is C2? C2 and C4 is. Tell me what we can do. What can we do? See, we know in case of series combination, charge is equal, right? So if there is some charge Q here, same will be here, same will be here also. Okay. We want charge on this one and charge on this one. So what we can do is, potential is given, potential is V. This capacitor C4 is 4C. Okay. So we can find out the combination, series combination. Okay. 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Right? Whatever is charged on this series combination, same will be charged on C2. Okay. Then we can find out that charge and divide by charge on C4. So 1 upon Cs is equal to, you have 1 upon C1 plus 1 upon C2 plus 1 upon C3. Right. So C1 is equal to C, C2 is equal to 2C, and C3 is equal to 3C. Okay. So what is the LCM? 6. 6C. So this has to be multiplied by 6. This one by 3 because this is 2. Okay. And this one by 2. 2 times 3 is 6 and this will be 2. Okay. 6 plus 3 plus 2. How much? 11. 11 by 60. Okay. Now this is, how much would be CS then? CS is equal to 60 by 11. Okay. And charge on C2, let's call it Q2. Q2 will be equal to what? CS times V. Okay. And charge on C4, let's call it Q4. Okay, Q4, it will be C4 times the same potential difference. Okay. So you have Q2 by Q4. You want that, right? Charge on C2 upon C4. So this is equal to CS times V upon C4 times V. VV gets cancelled. Okay. So this is, CS is 6C by 11 and C4 is, C4 is 4. 4C. Okay. So CC gets cancelled. It is 6 by 4, 11. That means 6 by 44, or you can say 3 by 22. So it is option B. Okay. This thing is clear. Good. Then 3 capacitors, each of capacitance C and of breakdown voltage V, are joined in series, the capacitance and breakdown voltage of combination will be? Tell me. They are connected in series. What will be net capacitance? Cs is equal to C upon N. How many capacitors are there? 3. Okay, if capacitors are equal, then Cs is equal to C upon N. So C by 3. Okay, and what happens to potential difference? This is first one, this is second one, third one. This is suppose V1, this is V2, V3. How much is net potential difference? V1 plus V2 plus V3. Good. So that is equal to V plus V plus V because they are all equal, right? So V dash is equal to V1 plus V2 plus V3, that is V plus V plus V, 3V. Okay, right. So this is very simple. Okay, or was it the most simple? No, there were some direct questions. All right, next one. A parallel plate capacitor is charged to a potential difference of 4 volts. After disconnecting the charging battery, the distance between the plates of a capacitor is increased using an insulating handle. As the result, the potential difference between plates, tell me, increases, decreasing, decreases, does not change. What are you doing? You are distance between plates is increased, right? Distance is increased. Okay. So what will happen to capacitor? Yeah. Epsilon naught Ka upon D. If D increases, C decreases. Right. So it is option B. Okay. Next one, a parallel plate air capacitor has capacity C. Distance of separation between plates is D and the potential difference V is applied between plates. Force of attraction between the plates of parallel plate capacitor is, tell me. How can you find out force? What times distance? Problem upon distance, you can say. How come? Work is force into displacement. No? Okay. Yeah. All right. So that is also fine. Uh, Here you have electric field. Okay, you have two plates. So one of them has positive charge, other one has negative charge, right? So you can say this one produces some electric field here. Okay. So other plate is kept in electric field of first plate. Can you say that? Okay. So how much is the electric field? Sigma upon 2 epsilon naught. This is field produced by one plate. Okay. Field of positive plate, I can say. So I will write electric field due to positive plate. This is the electric field. Therefore, force on negative plate due to positive plate will be equal to what? E multiplied by Q, charge on the plate, right? So it is sigma upon 2 epsilon naught multiplied by Q, and sigma can be written as what? Charge upon area. Okay, so we can say this is Q upon 2a epsilon naught times Q. Okay, and options are in terms of capacitance. Okay, so you can say that this is Q is equal to CV. So this will become C square V square upon 2 times A epsilon naught. But there is no epsilon naught here. Okay. So you can say C is equal to epsilon naught A upon D. We can use this, right? Okay. So epsilon naught A is equal to CD. So C square V square upon 2 times CD, C and this thing gets cancelled. So it is half of CV square upon D. Okay. Or CV square upon 2D. Right. Okay, so what's the answer? It's option D. It is option D. This thing is clear. Okay, good. Then let's see next one. The electrostatic force between metal plates of isolated parallel plate capacitor C having a charge Q and area A is. Option A, independent of distance between plates, linearly proportional to distance between plates, proportional to square root of distance between plates, inversely proportional to distance between plates. What's the answer? Option D. Right. Okay. C is equal to epsilon naught K upon D. C is inversely proportional to D. Next one, two metallic spheres of radii 1 centimeter and 2 centimeter are given. Charges 10 raised to minus 2 coulomb, 5 multiplied by 10 raised to minus 2 coulomb respectively. If they are connected by conducting wire, the final charge on smaller sphere is. Tell me. How will you solve this? Total charge will remain conserved, right? So Q is equal to Q1 plus Q2. How much is Q1? 10 raised to minus 2. How much is Q2? That is, this will be 6 into 10 raised to minus 2, because first one is 1 into 10 raised to minus 2. Second is 5 into 10 raised to minus 2. Okay. Now, when you connect the two metal plates, the two metal spheres, what will happen? The charge will flow from one to another. Okay. Charge will flow from one to another. Till what time? What is equilibrium? Till the potential becomes equal, right? So this is V1, this is R1, this is R2. Okay. This is 1 centimeter and other one is 2 centimeter. So V1 should be equal to V2. That means now there will be redistribution of charge. So V1 is K times Q1 dash upon R1. V2 is K times Q2 dash upon R2, right? So we want what? The final charge on smaller sphere. We want Q1. We can say Q2 dash will be equal to what? KK will get cancelled. Take R2 on other side. It will be R2 upon R1 times Q1 dash. Okay. But what remains conserved? Charge remains conserved. So Q1 dash plus Q2 dash is equal to what? Total charge Q. Yes, no. Okay, so that is equal to 6 into 10 raised to minus 2 coulomb. So Q1 dash is how much? Okay, we want to find it out, right? Q1 dash we want to find out what will be final charge. Q2 dash is how much? It's equal to this thing. So you have Q1 dash plus Q2 dash is R2 upon R1. R2 upon R1 times Q1 dash. Okay, and R2 is equal to what? R1 times 2, right? So you can say it is 2 times Q1 dash. Okay, because R2 is 2, R1 is 1. So it is just 2 times Q1 dash. This is just 2 times Q1 dash, and this is equal to 6 into 10 raised to minus 2. So 3 times Q1 dash is 6 into 10 raised to minus 2. That means q1 dash is equal to this thing divided by 3. Okay, so q1 dash is equal to 2 into 10 raised to minus 2. This is the answer. Got it? Yes, no? We solved similar question yesterday. Remember, there were two spheres having two surface charge densities. Okay, so what is the key thing when you connect two conductors? Till what time the charge will flow? Till the time the potential become equal. So there are two things to be remembered. One is the total charge remains conserved. Second thing, what happens? The potential becomes equal for both conductors, right? So this is true for capacitors. This is true for, I mean, conductors can be also called as capacitors. Okay. Then let's see next one. N identical mercury droplets charged to same potential V coalesce to form a single bigger drop. The potential of new drop will be. Tell me. What will be potential? So once again, we can say n identical mercury drops. So n times small r cube will be equal to capital R cube. So here they are combining, okay, coalesce to form a big drop, right? So what will be this R? R is equal to n raised to 1 by 3 of small r, okay? And now they are charged to same potential V. Okay, that is fine. So then now what will happen to the charge? So suppose charge on one small drop is equal to Q, or let's take small q. Charge on big drop, Q will be equal to, because there are n total drops and they are combining. So total charge will be n times Q, right? So what will be then capacitance? Oh, we just want potential, right? Yeah, we want potential, not the capacitance. Okay, so radius becomes this thing, okay, and you have capacitance is equal to what? 4 pi epsilon naught r, and that is what? P is equal to Q by V. P is equal to Q upon V, right? So that is equal to 4 pi epsilon naught R. Okay. So then, sorry, Q upon V dash. Let's call it V dash because for smaller drops it was V. So Q is N times Q and V is what? Sorry, not V. V dash is, let's keep it V dash only. Let's move it on other side. And this 4 pi epsilon naught R, let's move it on this side. So 4 pi, sorry, 4 pi epsilon naught times capital R is n raised to 1/3 of small r. Okay, so then you have n raised to 1 by 3. Take it in numerator, it will become minus 1 by 3. So you have n raised to 2 by 3. V dash is equal to n raised to 2 by 3 times q upon 4 pi epsilon naught r. So this thing will be what? Potential on small drop, 1 upon 4 pi epsilon naught q upon r, right? So it is equal to n raised to 2 by 3 times v. So this thing is clear. Okay. All right. So these many were the questions based upon this thing. Okay. So everything is clear. Yes, no.